Okay, let me see.
Recording in progress.
Can you see that? Or can you see my screen? Okay, can I start now or just wait for? Okay. All right. So good evening, everyone. Again, thank you so much for joining this course. So today, I'm going to talk about subsurface investigation method for infrastructure project and what are the different laboratory tests or in situ tests generally done. So, I mean, this is most important thing for any civil engineering project because we don't know what is below the ground, right? So we need to take out the soil sample and then characterize it. Mostly you bring the soil sample to the lab and characterize it. Sometimes you have to go to the site and do the in situ test. So today's lecture basically, I mean everyone knows, but I'm just going to refresh that that what are the different subsurface investigations available and what are the different properties you need to measure from the DBU samples. So what is subsurface investigation? So you see the proper civil engineering required adequate knowledge of subsurface conditions at the site of structures, so where the actual construction is going to be. So you need to go to the site and take out. So when you collect soil sample, you need to do the physical properties, and also you need to do the arrangement of deposit underlying material. So basically, you need to make a borehole, take out the soil sample, and characterize it, and then you need to know what are the different at different depth, what type of soil is there. Okay. So the field and laboratory investigation required to obtain this essential information. So basically, we need to, and then it's called the site investigation. Sometimes called subsurface exploration. Sometimes it's called soil exploration or exploratory program. So there are different names. So basically, is a subsurface exploration. Right. And so it's maybe physical weathering, chemical weathering, physical and chemical weathering process, and then what are the different transporting. So there may be transported soil and residual soils, and these are forms of millions of years. So we really don't know what type of soil below the ground. So when you construct any structures on any soil, we need to know what type of soil there. Okay, so that's the thing you need to understand. So basically, objective of this is site investigation to determine the location of thickness of the soil strata. So we need to know how much is the thickness of the soil. So it may not be so the soil. The current location, so maybe 50 meters away or maybe 150 or 100 meter, is totally different soil. And the soil layer is formed like a homogeneous. It may not be homogeneous. So it's maybe one layer, maybe thickness is more on the other side. So we never know what is there. Determine the location of the groundwater table. That is very important because the groundwater table fluctuates the soil properties. Again, all these dry unit weight, wet unit weight, bulk unit, all these things are going to change. Saturated unit weights, and everything is correlated. Recovery of the soil sample for the laboratory test. So when you take out the soil sample, how much is the recovery? So that is also important. So we'll be talking about whether the sample is representative or non-representative sample, and conduct various laboratory and field testing, and then also identify special problems occurs. Then preparation of a borehole. So boreholes is basically, you take out the soil sample. So you need to know for a particular site, depending on the type of the project, so how many borehole you need to, make, and then also at what depth, what should the spacing, all these things you need to know, and then put it in a chart for any particular borehole. So all the different properties, so that geotechnical engineer can see at one time, okay, these are the properties and what to do. So this is what you can say, this is like a blood test report, you can say. So name, and so what are the, the bore log should have all this name and address of the drilling company with the driller's name, job description number, number and type of location of boring, data boring, and then what type of sample taken. So whether it is auger boring, whether it's split spoon sampler, or thin walled Selby tube sample. So most of the time you need to write that. And then also where is that location of the water tables, that is also need to be mentioned. And if it is a rock sample, obviously what type of core barrel has been used, and also the actual depth of coring, and then length of core recovery. And also you need to find out from there how much is the rock quality. Rock quality designation. From rock quality designation, you can find out how much is the quality of the rock. So this is the just sample of bore log. So here you can see the project name, location, boring number, number of type of boring. So everything is mentioned. And over here on the left side, you see the description of the soil. So with the depth, how much, what are the different type of soil is there. And also the third column, you see the standard penetration number. So we have SPT value as N. So that should be corrected sometimes while taking this bore log, while incorporating the data in the bore log. So most of the time we use that the raw that SPD number. So then we need to do the corrections. So I'm going to explain that, how to do the corrections. And then also we need to measure the moisture content or water content. And then also you need to write, okay, SS, what is the sample? So basically the split spoon sampler. Sample has been taken, ST is the Selby tube, at what depth, and then also what are the different properties you determine. So this is same thing again, so N value, sometimes you can see over here the depth. So first one is the depth, description, legend, so different type of soil, and then also the sample is here, fifth column. You see the samples, whether it is D is for disturbed sample, whether it is U is for undisturbed sample. So that also need to be mentioned. Okay. And then also, as I mentioned, the earlier ones, the SPD N value. So N value is more, obviously, the soil is strong, right? And then also unconfined compressive strength also should be mentioned sometimes. It depends on what type of project. And then depending on that, people make a borehole and then log this data. So most of the time, people use SPD value, and then for any geotechnical engineering design, we need to know how much is the the cohesion or angle of internal friction of the material. Okay, for any design. So now the thing is, you have only this borehole and SPD data, nothing else. So most of the time we need to, there are several correlations that are available from SPTN value, how to find out that different friction angle or the cohesion. And then from there you can design, your foundation or any infrastructures. So basically, there are a lot of correlations that are available you can use to determine the shear strength parameter. So ultimately, we need to know how much is the shear strength, correct? And for any infrastructure design or foundation design. And then also, obviously, if you want to know that the consolidation stuff, how much is going to settle, so obviously you need to know that the Shelby tube sample, and then you need to use the consolidation test. So most of the project, depending on the type of project, so you need to do different tests. Obviously, people most of the time they use this okay, in a particular site, if there is a borehole data is already available in the existing building nearby, they use that as a preliminary guess. But if you want to do actual, the properties of that particular site, so you need to do this borehole. So again, the same thing over here. The project, so site exploration general strategy is the project assessment, literature search. So that's when you have an idea. Field reconnaissance, subsurface drilling and sampling, laboratory testing of the soil sample. So all these things, what are the testing to do in the lab? Project assessment, here, a few things you need to know: the type and location of the approximate dimension of the project development. So again, it's a small project, and the area. So you need to know how many boreholes you need to do. So that one also you need to check. Existing topography of any proposed grading. So we need to check also. And also any previous development. So previous development, if their existing site is already developed, so then you have an idea from the existing project. Then literature first you need to, for any if you unknown site, so we need to know the geology, obviously, what type of how the soil is formed. Again, this rock cycle, you need to know that igneous sedimentary metamorphic rock and how the different weathering process, all the different soil forms. So we need to know that. And then the soil survey report, geotechnical report, and historic groundwater table data. So also we need to know what are the fluctuation of the water table and the location of the groundwater table. Because this water table really, is very important because the properties of so dry you need to wait, to saturated you need to wait, or submerged you need to wait. So properties of the soil is going to change, with water. Then these days, a lot of remote sensing data there are these days, a lot of GPS, other things, people are using to calculate or to gather all this data. USGS also have their own data, available, but not too much detail. But you have an idea what type of soil is there in a particular area. So conventional aerial photographs people take, and also infrared aerial photographs. And then from there, depending on the vegetation and other things, people already correlated, okay, this type of plants or this type of vegetation, what type of soil is there in the particular site. So these will give you a little bit of idea. Field reconnaissance, obviously, any previous development or grading, etc., site topology, or any sign of slope stability, instability. Site drainage condition is also important. Also, the rock outcrops and site access. Field exploration, as I mentioned, so you need to go to the site and take out the soil sample on a particular site. So site boring layout, so you need to decide as a geotechnical engineer, so depending on the site, how many boreholes you need to make, what should be the depth, and a test boring or test pit, it depends on the type of material, what you want to know. Number of and frequency of the boring, that is also very important. And then how much is the depth, sampling method, and then also field testing. So this is field exploration. So this is the particular area. And then you see that the different, the dark circle, this is the boring hole location. So these are the different borehole locations. So most of the time we do the, the borehole where the actual foundation is coming, so that we have more control and we know what type of soil is there. So then you can design your foundation or any infrastructures effectively. Because if there is a thick layer of clay, we need to know how much is the length, depth of the clay, at what depth. So then you can calculate how much the building is going to settle. So all this information you need to know. So boring space, again, the site conditions and uniformity. So if the soil is, most of the time, the soil is not a homogeneous material, correct? So, different type of soils. And at the site, you'll not get the pure, like a coarse grain soil or fine grain soil or cohesive soil or maybe cohesionless soil. It is a mixture of different soils. And as I mentioned, like it can be silt, sand, gravel, and clay. It can be mixed with all this different material. So, and then also type of structures, what type of structures you going to make. So again, depending on the structures, you need to be careful. And then also typically one borehole part 2,000. So this is just like approximate guideline. You need to make 2,500 feet square part one borehole. And depth of borehole, that depends on the magnitude of the loading and the soil conditions. So these are some guideline again. So as you have seen, if the soil is very poor or erratic, because the soil properties are varies, then you need to do the lesser area. You need to do more boreholes, right? So if you have a soil is very high quality or uniform soils, similar type of soils, so then you can increase the area and the number of boreholes. Okay. So you see here one borehole every 50 to 100 meter of site for compressible soil of limited area. Then one borehole for every 200 to 300 meter, compressible zones of various ground surface. And then one borehole every 500 meter on the site of homogeneous ground. So the soil is homogeneous, uniform, so no need to do more boreholes. So then the spacing, approximate spacing of the boreholes. What should be the spacing between one borehole to another? So depending on the project, so you need to use different borehole, the spacing. So if you see the multi-story buildings, so again, these are the guidelines. Multi-story buildings, so 10 to 30 meters. So is a dam and dikes, obviously is 40 to 80 residential subdivisions. So highways is 200 to 500 meter. So these are the spacing of individual boreholes. And then how deep, also it depends on the surface conditions. And so again, if it is a poor, these are the equations. So second column is in meters, the same thing, and then third column is in feet. So if you know how many number of story you're going to construct a particular soil, and D is the anticipated depth of foundation. So basically, at what depth you are going to place your foundations. So you can easily calculate that how deep the boring should go. Obviously, most of the cases, if you are constructing a dam or if you're constructing a pile foundation or drill shaft or drill pier or any sensitive structures, obviously that you should go up to the rock. Okay, sometimes not even resting on rock, foundation. So it can be even socketed. Even you need to cut the rock and just inside the rock itself, some portion. So the soil boring, so obviously you need to take out the soil sample and then the trial pit, and then you need to make a hole using a drilling rig. So there are different types of drilling rigs that are available, and you can take out the soil sample from the ground. So then it's the boring or drilling or sampling, and then so what are the things? Subsurface drilling. Obviously, it is below the ground, or so it's subsurface. So it's auger drilling. There are different types of auger drilling: solid stem auger, hollow stem auger, post hole auger, helical auger, continuous flight skew augers. There are so many different types of augers. There are wash drilling also. People still use this wash drilling. There are rotary drilling, and there are percussion drilling, and there's Odex drilling. So again, depending on whether we're drilling only the soil or it is going through the rock. So again, if it's a rock, so then you have to use different cutting bit so that it can cut the rock. So this is a boring tool. Again, everyone knows, like a post hole auger, helical auger used to insert it into the soil. So just hand auger also. And then also obviously the power drill. So you need to using a machine so that it can bore, it can make a hole and collect the soil sample. So depending on the situation, so whether you're going to collect the soil sample. So most of the time people use, like I say, clay type of soil, use like a very soft push, not the hammer. So, just Shelby tube sample. If it is a SPD sample, it's a coarse grain soil. So, or clay mixed with, granular soil. So what you need to do, you make a hammer using a hammer, and then, and the sample will be collected using a core catcher and the switch spoons. Then you collect that sample later on. So these are auger drilling. So there are different, I will just show quickly different types of auger drillings are available. The hollow stem auger, how you can see here, there is the casing of the outer spiral, inner spiral rod, and also for removing pilot assembly for the inserted sample. And then maximum depth, it can go 50 to 100 feet. Okay, so this is how we collect the auger drilling. Then hollow stem auger, again, So that can get SPT test sample test results. Cannot penetrate very strong soil or rock. And then also it problem when the samples below the groundwater table. So groundwater table is there, so then you cannot use this. Is a problem. So there are different types of hollow stem auger. How it looks like, I already mentioned. So this is drilling with flight auger. Sometimes, most of the time, you just make a for any, just for example, pile foundations. Okay. So when the soil is good, you need to make a hole into the ground and then just take out the soil sample and shake it. The soil will go. If the soil can stand at its own, so without casing is required. So if the sample is going to collapse, so then you have to have that the casing. So this is again the washboarding. So use some water jet to make a hole into the ground, and then drilling rod and chopping bit, and there is a casing also there, and then you can collect the soil sample. Rotary mud or air drilling. So these are the different types of drilling. So basically, you can use rotary drilling, the beat at the end, the drill rod to rotate and advance. It can be used for soil and rock cutting by circulating drilling fluid. And also the common bentonite is and water slurry of density. So sometimes, when use that making a borehole, sometimes the sandy type soil is trying to collapse. So in that situation, use the bentonite slurry so that the soil can be stabilized. Okay? The cable tool drilling. So there are different types of, I'm not going to go in details. So rock drilling, coring or augering. So again, there are different types of attachment you need to add. So cut the rock, and then also depending on how much is the recovery of the rock, so you can calculate by using this the rock quality designations. Okay. The sample. Now the sample is so now you have seen that different types of auger and boring tools. You just collect the soil sample from the ground. Okay. The soil is collected from the borehole for testing, so it's known as soil sample. Now the thing is whether the soil is representative or non-representative samples. So the method of obtaining the soil sample is termed the sampling technique or simply sampling. The tool which used to collect the soil sample is the soil sampler. Okay, that is a sampler, and depending on the presence of soil constituted in the sampled soil compared to the in situ, the sample may be classified as representative or non-representative. So our thing is when you collect soil sample, whatever sample collects, whether it is representative or not. Okay, so representative sample is the one which there is no changes in the soil constituent. Sometimes the soils are different depths while hammering or anything SPT samples, the samples are mixed. Okay, so and then also while doing that, take out the soil sample. The structures of this soil sample is getting changed, or water content is getting changed, void ratio is getting changed. So if everything is maintained, then it's called a representative sample. Non-representative samples, if the soils are mixed or some of the soil constituent of the samples are missing. So sometimes when you collect the soil sample, if there is a water table in the sampler, soil sampler, the sample can fall. So in that case, that is not representative of the particular depth. Okay? The soil sample collected. So that is non-representative sample. So again, rock and soil sampling is the disturbed samples and then undisturbed samples. Okay. So disturbed sample is in place, structure is not preserved. So, but still you can do soil index properties like a liquid limit test, plastic limit test, particle size division test, all these things, the different physical properties test you can do. Okay. But for undisturbed sample, we need it, minimizes the effect of potential disturbance. So we need to do in situ density, okay, or in situ permeability, or soil shear strain, or the compressibility. Sometimes we need to do that for the undisturbed, undisturbed sample. We need to have undisturbed sample because you see, as I mentioned in the last class, like when it's a clay type of soil, clay has different fabric arrangement. So it can be floccular, it can be dispersed. So depending on that, although you can maintain the same density, in the lab, but you cannot really replicate the fabric. So that's why most of the time, the disturbed sample, the fabric arrangement is disturbed, and we need to do the undisturbed sample most of the time to measure this permeability. Just for example, and then go to the site and do the permeability test for better representation of the permeability value. The soil sampler. So there are different type of samplers you can use to collect the soil sample. One is the SPT or split spoon sampler, SP, split spoon, and one is Selby tube samplers. So you can collect the clay type of sample, piston samplers, and then heavy wall samplers. So there are different type of sampler. So standard split spoon sampler. So basically, it's a thick wall sampler, and it can divide into two half. And then also, while doing this, you need to hammer it into the ground. Okay. So over here, you see the diagram, the standard split spoon sampler, and then also when you do unassembled, it looks like this. Okay. So these are standard sizes. Everything is there. There is a cutting shoe, and then you hammer it. So now the thing is, obviously, if you want to collect the undisturbed sample, so you need the thickness of the sampler should be very thin, okay? And then also there should be cutting edge. And obviously, the design features governing that degree of disturbance of the cutting edge inside wall friction is also important. And the non-return valve also we need to check, okay? So how do you know the sample is really disturbed or not disturbed? Okay, so when you collect the soil sample, depending on the sampler is basically a tube, as I mentioned, correct? So we need to know the diameter of the tube. We need to know the thickness of the tube, correct? So for Shelby tube samples, the thickness is very less, so that you can push the sampler into the clay, and the disturbance will be minimum. So if you have a thick wall, and obviously, when we hammer it, the sample is getting disturbed, correct? So what you need to do, you need to calculate the area ratio, and you need to calculate the inside clearance and outside clearance. So if you know that the outside diameter of the sampling tube, if you know the inside diameter of the sample tube, then you can find out the area ratio. And if the area ratio is less than 10%, so meaning it's a good quality sample, okay? So these, and then the area ratio represents the volume of the soil displaced by the sampler as a ratio of the sample volume. And then the larger the volume of the ratio, the larger the sample disturbance. And most of the time, if the area ratio is 10, it's a very good sample. And sometimes area ratio up to 25% even considered to be good. So depending on the situation. So this is Selby tube sample. So this is a thin wall sample. So when you collect mostly the clay type of soil, just push it to the ground. And then you see there is a hole on the top of this, the Shelby tube. So most of the time, the bottom is the cutting shoe, it's this thinner one. And then when the Selby tube is done, when you are pushing to the ground, and you just make just take it outside using this hole over here. Okay. And then obviously, when you collect the soil sample, you need to put it in a vertical, put it in vertical, like as you collected the soil sample, in vertical directions, and then bring it to the lab. Okay. Piston sample, again, you see there's a piston over here in the Selby tube sample. So that will be just like the syringe, it can hold the sample, So minimize the sample disturbance caused by the back pressure. So apply some back pressure so it can hold the soil sample. Heavy walls, obviously, sample will be disturbed. Okay. Then also, this is important, the groundwater monitoring. So obviously, you need to use the standpipe using piezometer. And then there is a different type of sensors. So make a borehole and then put a sensor into the ground, into the borehole. And when it touches the water, it will give you immediately how much is the water groundwater level. So most of the time, you need to make a borehole depending on the site. If there is a clay type of soil, it is not that water will come to the borehole immediately. So we need to keep it for 24 hours and then measure the water. When the water level is steady, meaning that all the surrounding water already came into the borehole. So again, there are different perforated pipes, and sometimes we need to use that steel pipe with the grit, and then also sometimes you use the geotextiles also. So this is thin wall tube sampler, how it looks like. So as I mentioned, so we need to know how much is the outside diameter, how much is the inside diameter, and that is a cutting shoe. So we just push it to the ground, okay, to correct the thin wall tube sampler. So these are again what is the mechanism, the piston samplers, to collect the soil sample, and we're going to go in detail. Here, the rock coring sample, again, there should be cutting bit and the coring bit, and then also how to collect there should be the single tube core barrel and the double core barrel. And then when you collect the soil sample, using this the drilling or sampling the core, so you need to know how much is the recovery. Okay, sometimes if it is a weathered rock and the fractured rock, so you will not get exact intact rock sample. So depending on how much is the length of the coring, so you may not get exact the same length of the recovered sample. So so what you need to do, you need to take that the recovered sample, which is greater than 4 inches, and you add that all portion is greater than 4 inches. How much is the length divided by the length of the core? Okay, the total length of the core to recover the soil sample, the rock sample. So then you can calculate the rock quality designations value. So basically, you need to add that more than 4 inches sample recovered divided by length of the core. Okay. So then from there, you can find out if the rock quality designations is less than 25%, it's very poor. If it is 25 to 50, it is poor. If it is like a more than, if it is around 90 to 100%, is an excellent. So meaning if you have a sampling tube of this much length, so you calculate the whole length of the tube, the recovered sample intact. So that is like an excellent intact sample. But sometimes you may not get that because of the fractured rock and weathered rock, depending on, again, what type of rock is there. So it may be sedimentary, it may be igneous, it may be metamorphic, all these, or maybe slate, different types of rock there. So depending on the rock, you will get that different type of RQD values. So now, there are different in situ tests. Again, I'm just going to go all these different tests. It's very common, as I mentioned, the SPT or standard penetration test. The value generally denoted by N, capital N, and from N value, you can find out if the N is more, meaning the soil is strong. Then the cone penetration. So we have a standard cone. You just push it into the ground, and you need to know how much is the end bearing, and then how much is the skin friction or tip resistance and the skin friction. Easily you can calculate from there what type of soil, and it is connected to the computer. Easily you can find out. It's very quick. Only disadvantage is cone penetration. You will not get the soil sample, actual sample, but it will give you an idea what type of soil is there below at what depth. Vane shear test, sometimes the soil is very soft. Even when you collect soil sample from the field, the sample is already disturbed. So then what you need to do, you need to go to the site and do the test there. It's called the field vane shear. Sometimes you can do the test in the lab, so the lab vane shear. Pressure meter test, also it is in situ test. You go to the site, use the pressure cell, make a borehole, and then apply pressure. And then what is going to happen, how much is the resistance from the side. The soil is strong, so it will more resistance is going to offer in the lateral direction. So you can find out from there what type of soil. And then also the flat plate dynamometer, so similar type of equipment. you can use that. And then the borehole shear test, also the plate load test. Plate load test, again, you go to the site and then do the test at what level the foundation is going to be, and you just put a plate, standard plate, and then apply load. And then obviously you can find out the load settlement graph from there. And depending on what type of soil, there are different correlations that are available. So if you know how much is the plate size, how much is the settlement of the plate, then you can find out if you know how much is the width of the foundation, or if you know the width of the foundation, then you can find the actual foundation how much the foundation is going to settle. So all these things you can easily find out from the plate load test, or the field test. The lab, go to the site and do the field test, the plate load test. So these are, as I mentioned, this SPD value, the standard penetration test. There is a standard test, there is a standard hammer, and there is a standard height of fall, and just put it with the ground most of the time. So so you need to calculate the first 6 inches, you ignore the second. So I'm going to go in details. And then the vane shear test. The vane shear test is when the soil is very soft. You have a vane, is basically this like a cross type of stuff. So we just rotate, apply some torque. So you need to, when you know how much torque you have applied. So the shear, it will be forming a cylindrical surface, and then you need to know how much is the resistance, how much torque you applied. You need to know how much is the resistance applied around the periphery of this the shear. So, and then also at the top and bottom, so you can easily calculate how much is the strength of the soil. Then the pressure meter test, as I mentioned, so we just apply pressure on the lateral direction. So how much is the resistance offered on the side? So easily you can calculate how much is the stiffness of the soil. And there are correlations. The CPT, as I mentioned, is the cone penetration test. So you can just push it into the ground. You can also collect the soil sample using, if you attach a special attachment, most stuff, you can attach it, and then you can collect the soil sample also from there. And then also that the diameter test. Okay. So, and then also the dynamic cone penetration test is also there. So it is people are using this, but there is a standard hammer, and then just fall into the ground. Depending on height of fall is 575 millimeters, depending on the soil type, how much the penetration there is a relation between that. From there, you can find out the dynamic penetration index. So obviously, and you can easily calculate. You have an idea what type of soil at the site. So these are different boring, as I mentioned earlier. So few things, as I mentioned, when you collect soil sample, we need to check that how much is the recovery ratio. We mentioned that area ratio. We need to know the recovery ratio, the actual length of the recovered sample divided by theoretical length of the recovered sample. So this one for the soil, this is for the soil. Again, LR is equal to 1, indicates the sample is relatively undisturbed. So if LR is more than 1, the sample is expanded or loosened. So that one you have an idea. So again, this is for the soil. For the rock is different. For rock is how much is that more than 4 inches. You can add all this and then divide by total sample length. SPT is, as I'm just going to tell, this is very common thing people use, and most of the borehole people have that, just only the SPD value. SPD is the hammer is 63.5 kg hammer, and the height of fall is 76 centimeter. And so the total penetration is 6 inches plus 6 inches and 6 inches into the ground. And we have a standard SPD sampler. So just 6 inches plus 6 inches. The first 6 inches you just ignore. And every 6 inches penetration, you count the number of blows. So that is N value, that is the raw N value. So first 6 inches and the second 6 inches, you calculate how many number of blows, you just add that to, that will be the actual SPD value. Okay. So what is the advantage of this SPD test? Is inexpensive, is availability, sample off-chain, huge database, able to penetrate local hazard. Okay. And then disadvantages: operate independent, accuracy is poor, not good for gravel, so it will be difficult to penetrate. no continuous profile, no good correlations for clay. Again, for clay, we cannot just use that. So because you need to use this Selby tube sampler. This is how it looks like. Split spoon sampler. So this is so it can divide into two, and then also there is a cutting shoe over here, and then you see there is a core catcher over here. The core catcher that should be attached like over here. You see the my pointer here, so that should be attached there. So most of the time when you push it, this will just open up, okay, and then when the sample is inside, just is closed. So when you lift it up, the sample will not fall. So that is core catcher, and then you can collect this, soil sample from there. So these are, how it looks like, this, the core catcher, and then when it, as I mentioned, it open up, and then it can hold, the sample. So there are different types of hammer, again, depending on the location. So how the hammer is lifted, and just do like this, just whether you lift the hammer manually or just using crane and just drop it, okay? Or using some machine or pneumatic tools and then just lift it up and then do this. So depending on the type, and so that's why there are a lot of corrections is required for SPT N value. So over here, so you see the boring of, so basically at what depth you need to do, okay? So the 50 blows are required for every 150 millimeter or increment. It's 100 blows are often to drive required 300 millimeter or 10 successive blow procedures, no. So when you do like your number of blow is more than 10, and that is sampling, it is not advancing. So then you have to stop, okay? So no need. So then, depending on what type of hammer you are using, what is the efficiency of the hammer, so then we need to do the different corrections, okay? So, so most of the cases we do, if the efficiency of the hammer is 60 to 70%, and do the correction for that. So again, the energy ratio is the actual hammer energy to the sampler divided by input energy times 100. And then also, as I mentioned, so you need to do the correction. So sometimes N60 or N70. So there are different, you see the N70 is CN, that is the adjusted for the effective overburden pressure. And then N is the one actual raw in value. And then mu1, mu2, mu3, and mu4, these are the different correction factor or adjustment factor. And that depends on over here, okay? So this can be for the hammer, different type of hammer has different correction. Depending on the rod length, sometimes you have to attach the rod if you go deeper depth. So most of the time is 1 meter, 1 meter, 1 meter, you attach it. And then the sample corrections you need to do, the borehole diameter correction. So all these different thing correction you need to do, and then you will get that. And then also depending on the efficiency of the hammer, N60 or N70. So then you will get that, the actual corrected in value, okay? And as I mentioned, so over here, these are the relations with the angle of internal friction with the corrected in value. As I mentioned, we need that C and phi value for any design of foundation or any structures, okay? So the number of correction applied to the recorded number of blows, so as I mentioned, the efficiency of the driving system, what type of hammer you use, length of the driving rod, overburden pressure, this is very common. And then also we need to use the water table, okay? Then the cone penetration. The cone penetration is less robust than SPT, much faster, obviously. And only thing is no sample collection. So this is mostly people use the Dutch cone. The Dutch people, they started. So that's why we sometimes call the Dutch cone. The angle is 60 degrees. Just, there is no hammer, just push it into the ground. And then depending on, you need to measure how much is the tip resistance. So most of the time, the soil is granular type of soil or cohesionless soil or sandy type soil. So then the tip resistance will be more. If the soil is clay, the tip resistance will be less, but there will be friction will be more, and the slip friction will be more. So with the depth, you can find out what type of soil below the ground, okay? So, and then you can find out the friction ratio from there. So you see the QS is how much is the, the tip the skin friction, and then QC is how much is the cone penetration. Okay, so from friction ratio, we can easily find out what type of soil is there at the particular site. And the direct application to the piling, so we can do that. And then also the E is a function of over here, the QC again. So here, how it looks like. So again, there are electric cone and there are piezo cones. There are different samples. These days, people are using even for the seismic stuff into that, so that you can get the data for the seismic GS, modulus from there. So over here, again, as I mentioned, this is developed in Netherlands, further developed. So basically, it's a mechanical cone. There are electric cone and then also piezo cone over there. So this is how it looks like. It is mounted inside the car, and then also the sample. These are the different the length of the tube, and then basically at the bottom of the car, the pipe is going down and then push it into the ground. Okay, and obviously sometimes to push it into the ground, obviously you need to anchor this car itself, into the ground so that you can push it into the ground. This is how it looks like over here, and the sample is pushing. This is how it looks like the cone. So and then this is a closer view. This is the hole over here that the cone CPT cone is really penetrated into the ground. And then again, it will give you advantages. It's very quick, and it will give you the two things. One is the cone resistance or tip resistance, and then also it will give you friction, slip frictions. That is the instrument is inside that, and you will get the skin friction. So and you can find out the friction ratio, how much is the slip friction divided by how much is the cone resistance. You can easily calculate from there. Okay, and then also it will give directly all these three different values. So sometimes, if you go deeper depth, so the cone, instead of going vertically, it may a little bit of tilt, and that may go really totally different directions, and it's not vertical. So, but that the monitor computer screen, it will give you how much is the angle of inclinations. So if it is more than 10 degrees, so we need to stop that. Okay, you need to do it again. So if it is more than 10 degrees, so it should be, then it is, it will not be vertical. It will higher depths, and then it will be totally inclined. So and then it will give you automatically the cone penetration and the skin frictions and at what depth. So you have an idea. So most of the time, this is the typical data. So you can find out. So obviously, if you see in a particular site, the penetration resistance is more, meaning that at particular depth, there is a sandy type soil. If you see that at particular depth, the skin friction is more, so obviously that particular depth, the clay is there. Okay, so you have an idea. So obviously you need to read this system carefully. So over here, the same thing over here, you see that how much is the total. So obviously how much is the skin friction, how much is the shear velocity, you can find out from here. And then how much is the pore water pressure also you can find out from this data. So again, most of the time you will get these two, and with the depth, how much is the cone resistance? The cone resistance, how much is the skin friction? So easily you can find out these two data, and you have an idea what type of soil below the ground. It's very quick test, and easily you can determine. So no need to take out the soil sample, and then do analyze it and then find out. So, and then you can find out the friction ratio. There are a lot of correlations that are available, CPT and SPT, and then also there are, if you know the CPT, SPT value, there are different design charts that are available. How much is the bearing capacity of the soil? So easily you can calculate or design your structures. Okay. So as I mentioned, so the cone penetration resistance, you can find out how much is the total force and how much is the area of the cone. And the same way you can find out how much is the side friction. So side friction, how much is the friction, total friction divided by the area. So you can easily find out that how much is the friction. Two things you need to calculate. And then also you can calculate how much is the friction ratio. That one you can calculate how much is the tip and how much is friction, and then also slip friction, how much is the cone resistance, you can calculate also from there. And from the friction ratio, if it is less than 1, usually sand. If it is friction ratio is more than 5 or 6, then it is usually this is clay or peat soil. As I mentioned, there are a lot of relations that are available, the friction ratio and the normalized cone resistance. For for most of the time, the friction ratio is more, as I mentioned, is more ratio, meaning it is more towards clay. And if the cone resistance over here on the y-axis, cone resistance is more, meaning this is a granular type of soil, or you see here on the top, sandy gravel, gravelly sand. So it is more coarse grain type of soil. So you have an idea from this graph. And then from the undisturbed or undrained shear strain, there are correlations that are available, so you can find out from the CPD. And there are, as I mentioned, there are a lot of relations that are available from this. So most of the time, either you do CPD, either you do SPD test, and then ultimate aim is you need to find out how much is the shear strength parameter, that is CN5 value. So that's the reason there are several relationships available. So if you know this, like from the CPD value, the cone resistance, how much is the stresses, so you can find out how much is the angle of internal friction of the material. So there are several relations that are available, so you can find out how much is the undrained shear strength of the clay using this cone resistance. Again, the vertical stress and the cone resistance. So there are different the cone bearing values are available. I'm not going to go in detail. There are CPD of the soils. Again, the cone resistance and friction ratio. There are people have developed the Lunar and Christopherson. They have done a lot of relations. If you want to read more paper, so they have they developed a lot of relations. SPD, there are some relations are there. SPD and CPD also. You can find out. The SPD mostly from the, if you collect the soil sample, you can find out the particle size division graph. And then also for the cone penetration, no need to collect the soil sample. So basically, you can find out how much is the cone resistance. So there are correlations over here. You can find out SPD versus CPD. And then also, as I mentioned, the more sophisticated instrument, the seismic piezo cone. You can use that to find out, again, the slip friction. And then also advantage is here, you can measure the pore pressure. Okay. And then also the shear of velocity you can find out. Okay. CPD versus SPD. CPD advantages over is basically you can measure the pore pressure, you can measure the dynamic soil sample soil properties. It's more reliable. CPD disadvantages does not keep sample, but you can using most stuff sometimes. Will not work with soil and soil with gravel. If it is gravel, you cannot penetrate the cone, and need to mobilize a special rig. So obviously, sometimes when you need to push it to the ground, no hammer, right? So we need to have a special rig. So first we anchor the whole system and then push it to the ground. Diameter test, again, this is just push it to the ground, and then there is a system. So we just apply some pressure there, and from this, how much is the lateral confinement. Depending on that, you can find out the stiffness of the soil. And then also there are, so we have 1 or 5 minutes, maybe 2-3 minutes. So the last method is, I'm not going to go in detail. There are geophysical methods. So again, so obviously there are indirect methods. This is indirect method you can do, or sometimes. So one is the seismic refraction method, a cross hole. It can be downhole method. Electrical estimating methods, there are a GPR, ground penetrating radar method, or electromagnetic induction method. So most of it is seismic refractions. So what you need to do, basically, we have a geophone, and you have just hammer a particular site, and then you have a special geophone. So obviously, the velocity will transfer, and then you collect every geophone, and you can collect from the data, you can find out how much is the different the depth of the different soil. Okay, so and this one is, it can be single one, it can be multi-channel. So there are different channels are using this seismic refraction method, and from there you can easily find out for the shear wave velocity there is a relations. And then also shear wave modulus. We are not going to go in this detail, but if you want to design, you need to know that the G value, shear wave modulus, and then the shear velocity for the different type of soil. You have this shear wave velocity. So from there, you have an idea what type of soil is there. Okay? So basically, from the shear wave velocity, if you know, and then you can calculate the different depth. So obviously, if the soil is very strong, it can, the wave can propagate quickly, right? So and then spectral analysis of shear waves is the same thing. Again, you use multi-channel analysis for the shear wave. I'm not going to go in detail. Electrical resistivity also you can use to find out what are the different soil layer. And then again, this is the 4 electrode method we used. And then from there, if we have passed the current and the voltage, you can find out the apparent resistivity. And from there, you can find out what type of, the layer 1 and layer 2, you can easily calculate what type of soil is there. Again, for different type of soil, the resistivity of the soil is different. So from there is the standard charts are there. You have an idea what type of soil there. Okay. So I think that's all for this, the sampling or subsurface investigation techniques, various subsurface investigation techniques. Okay. All right. So yeah, I know that I just go quickly, so there are so many. So basically, the borehole is most important. So you collect the soil sample using different sampling technique, and then just put it in a bore log with the depth and what type of sample is there, what type of, mostly it is N value is there, what is the location of the water table. That's the main thing. As I mentioned, this is like a blood test reports. If you have more confident of your bore log, then you can design your foundation or any structures more economically. So most of the time in geotechnical engineering, if you don't confidence with your data, use more factor of safety. That's all. Geotechnical engineer generally you use more factor of safety when you have when you don't have much confidence on your geotechnical data. So it may not be economical, but most of the cases, geotechnical structures, we don't want any failure. So I mean, if it fails, then it is a problem, right? So there are methods to rectify these days, but much more expensive. Right. Any questions on this? Again, this is everyone knows this. I'm just just revising all this. So for any geotechnical engineering design, we need to know this. All right.
Sir, I wanted to ask one thing. In the MASW that is mentioned, you have mentioned in your slide that inversion.
Okay.
Sir, can slide details, sir? Actually, I will be using, planning to use in future. So,
okay.
Slide details, sir, if you can highlight a few things.
Okay. So here, I mean, I can say, because with the time things, we have not explained. I just mentioned that all these 4 methods, that's all. I have not explained anything at all, for the indirect methods. So most of the time, for these seismic things, I used several times in US here. So most of the time, so we need to really know the softwares and stuff. So that one, basically there are several channels. We need to make a hole, and also sometimes we need to use the borehole, and then the receiver should be inside the borehole also. So there are different techniques. I can send some material to you, maybe, and then we can explain in much more detail, Okay.
Okay, sir. Thank you.
So this is just, I mentioned just only this, what are the different methods. So most of the cases we use that one geophone and then hammer it, and then just hammer it, and there is several geophones. So it will travel, right? So it will go to the one layer, it can go next layer and then go receiving. So most of the time, how much time and the shear velocity you can easily calculate. And again, if you are using that the seismic one, so we need to you can there are instrument is a little bit different, and then also the most important things is you need to really know how to interpret the data. So So using the
Agreed, sir.
software.
The
Sometimes,
frequency,
yeah.
etc., and time history,
Yes,
and all
yes,
those
yeah,
things
all
we
these
have
things.
to look into. Agreed.
Absolutely, yeah, absolutely. And also sometimes, you know, there are a lot of noise, and you need to remove that noise. Otherwise, you will think this is a soil, different type of soil. So you need to be careful while analyzing the data.
Yes, sir.
Yeah.
Thank you so much, sir.
Mm-hmm.
Yeah, so my question is, just wanted to know the basic difference between SPT and CPT, and which is more convenient to use at site. Now, apart from the difference in results, which is more convenient and which is most preferable.
Okay. Again, geotechnical engineer, it depends on availability of the equipment. Sometimes, I'm in Southern Illinois, even in Illinois Department of Transportation, although we know that SPT is better, depending on the site, but it's more sophisticated. It will give you the result immediately. But people still use the SPT method. It's very common over here. It depends on the availability of the equipment, and obviously, if you want to, the CPT is more sophisticated. I think a lot of DOTs over here in Illinois, in US, people are using CPT value, and then also there are correlations are there. So most of the cases, SPT value is easy. Instrument is cheaper. Just only thing is just hammer it, and then 6 inches, ignore 6 inches, another 6 inches, count how many number of blows, and you will get the SPD number. Obviously, you need to do the correction. So depending on what type of instrument, hammer you use, efficiency of the hammer, all the correction you need to do, either 60% efficiency or 70%. So you can do the corrections. Other hand, CPT, just push it to the ground and you will get it automatically. But only thing is you cannot use that for totally gravel type of materials. You cannot penetrate. So it is, that is the disadvantages. And also, although it will give you everything, so it will give you a graph. So if it is a cone penetration end bearing, so it will give you more value, meaning it's the sand, or more sandy or cohesionless soil. If it is the slip friction is more, so in the computer screen itself, so it will give you automatically. And I used, when I used to work for a Dutch company, so I used to do that CPT every day, every 50-meter grid, and most of the time we fill it with sand for the dredging. And then we used to do everyday CPT, and it's very quick. It will give you automatically how much is the slip frictions. Only thing is you have to attach 1 meter, and when you go deeper, you have to stop because it may, it is not vertical. So the angle of inclination is more than 10. So disadvantage of CPT is you will not get the sample, but again, as I mentioned, there is some attachment. So you just push the cone, and then detach the cone, and then push the tube again, and then you can collect the soil sample. And the only thing is you cannot attach the thermostat there, so that the core catcher there. If there is a sandy type soil, that will fall. If it is a clay, then it is fine. So that is the disadvantages of this CPT value.
Yeah.
Does it make sense?
Yeah.
Again,
yeah. We also prefer SPT at site. Most convenient to use.
I mean, yeah. If you get the sample, it is cheaper, but again, depending on the availability of the instrument also,
Yeah, true. Thank you, sir.
All right, thank you. Any other question? Okay, so then I mean, whatever, I need to share the screen and that's all. But the next session is, there are a lot of things. I have to, go quick, So you want like a 5 minutes break now? Yeah, okay. Yeah, okay. So now it is like a 7:40. No, not 7:40. Okay, 7:36. Okay, so I'll join soon. Okay. Okay. All right. Thank you. Stop sharing now. All right. I think it's time now.
Recording in progress.
So you have to go very fast, so that to cover all these things. So anyway, welcome back. Good evening, everyone. So now in this session, I'm going to talk about the soil ground improvement by drainage, different dewatering methods, a technique, and then consolidation of soft soil. I don't know whether I should cover this because everyone knows, but I may go quickly. And then the foundation treatment method for soft soil by using surcharge or PVD, surcharge or preloading. And then we will talk about the vertical drain. One is the sand drain, one is the PVD, the prefabricated vertical drain, and then also talk about the vacuum consolidation. So there are, I have to go really quick to complete all this. So now, as I mentioned, it is get rid of the water, right? So dewatering technique. So first thing is, what is the effect, the detrimental effect of water? Okay, in geotechnical engineering, it reduces the soil shear strength and stiffness. Okay, increase the soil weight. Sometimes increase because the soil is saturated. Unit weight is increased. Generation of excess pore pressure, that you don't want that. So for any infrastructure, so anything is the pore pressure, again, you have to go to the soil mechanics, that the pore pressure increase means the effective stress decrease, and then it's not good. Necessary conditions for liquefaction, development of uplift flow, some water will give you uplift pressure, that is not good. Increase of lateral earth pressure. So again, that's why, for back lateral earth pressure design, we use granular type of soil, all the water drained out quickly. If the water is there, the water will give you additional load. Soil expansion happens, expansive soil or soil collapse. And then erosion of the soil particles takes place, and then also freeze and thaw, because the water is the one. If there is no water, there will be no freeze thaw, So so now the thing is, water you cannot control the rainfall, water table, so we don't have much control. So then what are the different methods to control the groundwater? One is the drainage, and then you just drain the water. And then obviously we need to use different type of pumps and and then depending on the environment of the soil, you need to check. There are different dewatering techniques we are going to talk, and then also the barrier system. We just really cut off the water, okay, by using different things. So it may be sheet pile, it may be the bentonite barriers, all these things. But then again, we are not going to talk about that over here. So just for example, as I mentioned, there are 3 examples. One is the drainage. So again, mostly the retaining walls, so we put a drainage filter over there, and then using just like a coarse grain gravel there, and then also they put a geotextiles on the top layer, and there is a pipe. So that's how we just the drainage only, so that on the retaining wall, all the drain water will go. Dewatering, again, using some type of pump to get rid of the water. So if you want to construct in dry situations, so construction in dry situations, you have to just pump the water out to the original water tables, go down, and then you can do your construction in dry situation. And then the barriers. Sometimes we need barriers, so we are not going to go in details over here. Just for example, some pavement generally fell because the water table fluctuation. There is a drainage is not proper. Sometimes we do some barriers so that the water really cannot go up, and then they create a problem to the pavement. Okay? So these are like a well point system, watertight barriers. So these are things I'm going to go in much more details now. So now the thing is, why we need that the groundwater. So how to control the groundwater the excavation at the excavation site. So groundwater is usually regarded as one of the most difficult problem in excavation work. And then also to remove the water, so we need heavy and continuous pumping, and that is expensive. So it may, and also when you drain out the water, sometimes the surrounding structure may subside or settlement. And then also the process, the removal of this excess water from the saturated soil mass is known as the drainage. So this is called the drainage or dewatering. So we'll go more detail what are the different the dewatering method. The process helps us increasing the stability of the in situ soil mass by reducing the seepage and the water pressure. So the various civil engineering construction, sometimes we need the excavation need below the water table. And these are the special situation while you excavate the basement of a building or lying foundation of a dam or bridge or excavating a drain, where the water, we encounter water table. So we need to remove the water, we need to drain the water so that the water table is going down, and then or for laying sewer lines, okay? So all these situations, all such excavations do require lowering of groundwater or water table below the bottom of the excavation. So now how to do that? There are different methods to do, okay? So the dewatering or control is obviously the groundwater can be defined as the water held temporarily in the water soil above the water table, the groundwater. Dewatering is a process to lower down the water table reasonably dry working conditions, especially for the excavation activities. So that can be temporary, it can be permanent. So most of the cases, the temporary is exclusion of water table by lowering down the water table. Permanent, generally we do the cutoff wall or the flow of groundwater. Most of the cases you use geoenvironmental applications. We use that slurry trenches. So purpose of dewatering is basically, you do the construction when its water table is really up. So we need to remove the water table so that you can construction can be in dry situation. The permanent dewatering system are far less commonly used for temporary or construction dewatering system. Most of the time, you just temporary, and then when the construction is done, it's fine. The structures is done. There's no problem. The common dewatering methods or dewatering techniques is basically this again, everyone knows this, various methods of dewatering groundwater: pumping from the open sump, pumping from oil point, pumping from bore wells, pumping from deep wells, and then also pumping from horizontal wells, and electroosmotic method to lower the water table. So again, what method you're going to use, that depends on the site conditions, what type of soil is there, what is the permeability of the soil at the site. So that is very important. And then also the extent of groundwater depends on the subsurface stratification. That is important, very important. Presence of water-bearing strata, where is the water table located? Aquifer permeameter or in situ permeability. So that's again, while doing this well bore, so we need to know what type of the confined aquifer, unconfined aquifer, all these things you need to know, or parched aquifer. So this is like a open sump, pumping from open sump. So you just make a hole, and then so obviously the water will go. So obviously the water will from higher depth to lower depth, it will go, and then it will just deposit it there, and use pump to remove the water. Okay. So obviously you see our initial water table was here, and the final water table is going over here. And obviously when doing this, the sump pump, and then you need to have some filter type of design, so that otherwise you'll be, pumping clay with salt. So we want only pure clay. So that's why in the figure over here, you see the gravel. So that will just only the water will, you can pump. Then advantage of this method, open sump, you can not more than 8 meters below the pump. Okay, that's the limitation of this. So, and when you can use this, when the site area is large enough to permit excavation and cutback is stable slopes, it is easy. And there is no important structures close to the excavation. It might damage the settlement resulting from the erosion and due to the water flowing towards the south. So that is important. So again, this is very easy method, but the limitation is it if you want to reduce the water table below 8 meters, it's not possible. As I mentioned, the filter design. So we're not going to go in detail. So most of the time we use like a granular type of filter. There are geotextiles filter. So you need to design that. So in the wall, so basically when you need to put that most of the granular filter, so that when you pump the water, you just pump only water only. Okay, I'm not going to discuss in detail over here. And then also the filter design. So I'm not going to go. So then the second one is pumping from well points. So what you do, you just make a borehole and then pump the water out. So what is going to happen? Obviously, you see the standpipes over here. These are the observation boreholes. And then you see the original water level was here. And now it will forming an inverted cone, okay? And then obviously, so how much is the distance from this inverted cone? So that will be the radius of influence. How much is the radius of influence for one borehole? So beyond that point, there will be no reduction in the groundwater table. So here, well point. So depending on the area, you need to choose how many number of well point you need to use and what type of pump you need to use. A lot of things in design problems. So, but this is very basic things. Sometimes you need to use the multiple lines of storage well points required for except more than 4 to 5 meters below the groundwater table. Okay. So then this is how it looks like. So there is a header pipe over here. There is a riser pipe, and there is a well point is here. So basically, this is just only one, and all there may be several of that well points that will be connected to the header pipe, and then the header pipe is connected to the pump, and all the water will be removed from there. This is a single stage well point system, how it looks like. Then again, how to calculate how much is the water is coming out from the well. Again, everyone knows how to calculate that using the Dupit-Thiem's approximation. So again, QWQ, this is the equation for unconfined aquifer. There are unconfined aquifer, confined aquifer, and sometimes you need to, this is for the well is penetrated up to the full depth. And there may be equation for the partial penetration. I'm not going to explain that over here. Most of the time, you will use that the equation for full penetration in unconfined or confined, the equation you can find out. So the total, the quantity of water, again, is based on that Darcy's law. Easily you can find out that Q is equal to Ki, how much of the water is going to be coming out. So, so over here, the K is the most important, the permeability of the soil, surrounding soil. And so the equation, the first part is, this is ln, so obviously the log base E. So if you want to use log 10, that there will be factor 2.303 factors, you need to use it in front of that, the equation. So this is for unconfined layer. This is for the confined layer, how to find out for the single well, how to find out the discharge. So this is a standard equation you can calculate. So basically, you need to know how much is the diameter of well, how much is the the distance from the influence, how much is the influence radius, influence zone. After that, there is no water table reduction. So you need to know all this, and easily you can calculate. So the drawdown curve, how it looks like. So over here, the one side well points is the one point. Initially, you see the water table was here. Now, because of this well, so now the drawdown curve, this looks like, that the inverted cone, as I mentioned, the final drawdown curve is there. So basically, if you want to do excavation, so do something, construction at this point, you can easily do it. So this is like a two-sided well points, how it looks like. It's a similar symmetrical structures. This is, the water table is finally below. So initially water table was here, now the water table is here. Okay. So you can do this part, the construction over here up to that depth, in dry situation. So there are a few things you need to know about the well point system. So the groundwater installation of the filter well, number of filter wells, usually 1.5 to 1 meter long, 5 to 10 centimeter diameter. Okay, and the vertical riser pipe is connected to the header main. And here in this cases, the water can be lowering water 5 to 5 meter below the level, generally regarded practical limit. That is the maximum limit you can go. The well point generally spaced between 1 meter to 1 meter to 2 meter. And if it is more than 6, you want to remove the water level more than 6 meters, then you need to use not only the single points, you need to use multiple points. Okay. And then if you want to do the reduction or lower the water table more than 16 meters, then you have to use the deep well system. So there are single method, single well point, multiple stage well point. If you want to go deeper, then use a deep well system. This is like a well point system, how it looks like. This is a well point, and there is a, as I mentioned, the header pipe and the riser pipe. There may be several riser pipe will be there, and then for multiple system, and then how much is the original water table, and now the after the dewatering technique. So this is the water table, is the final water table. So this is deep well system. Again, deep well system generally uses submersible pump. And there is a PVC casing, and then you need to, and then on the top there is a bentonite seal, and there is a riser pipe, and then the header pipe should be connected. It's the same concept, but only thing is a submersible pump will there, and that can pump because it's really deeper depth. Okay, so pumps at the place at the bottom of the well, and they are more powerful than the well points. It requires wide spacing and fewer well holes because it's a deep one. And they're used alone or in combination of the well points. So this can be used as a deep combinations, and it can be just the pump on the top and then well, So these are the few things I just want to mention over here in deep. So there are, you can use the chart or nomogram for the well point spacing. So you can from the groundwater. So you need to know how much is the groundwater reduction you need. And the second column is, you see there is a spacing of well points, and the last column you see what type of soil. So depending on what type of soil you are working on, whether it is uniform sand and gravel, this chart is for the clean uniform sand and gravel, and then you want to know how much is the lowering of water table you need, and just draw a line, and you can easily calculate how much is the spacing required. So this graph is nomograph of uniform clean sand and gravel. And then there are nomograph also for non-heterogeneous sand and gravel. So maybe in the tutorial today, I'm going to solve one problem using this graph, a chart. Single well point system. So as I mentioned, this is a maximum. It can go up to 5.5 meters. And, so, and then if it's a single point, so you can do the multiple stage. So you can do how the water table can be reduced. So initial water table was here, and then the final water table is here, is quite low. So you can do the construction in dry condition. So sometimes, as I mentioned, so you can use the well point and also the deep well together. Okay, so the well point, because the capacity is less, so you can use 3. So you can do just only the deep well, only 1. And then the water table can be reductions is a greater extent. So this is the combination you can use. You can use multiple stage, all well points. You can use well points and also the deep well together. So, and then this is another method to the deep well system. So the same thing over here, that is chart. The deep depth of excavation is more than 30 to 40 feet, and usually spaced between 20 to 200 feet from center to center, and between 8 inches to 16 inches diameter. And also, so you can see here, the well screen may be used 22 feet long, surrounded by the sound gravel. So again, depending on the situation, what type of soil is there, so you can use that, the well screen. Then the vacuum pump can be used. So here for the fine grained soil, so permeability is less than between 0.10 to the power minus 3 to 10 to the power minus 5 centimeters a second. Necessary to apply suction head, excess head of capillary head, and then also to create a vacuum for the sand filling. So we have a sand filling and then the sealer, and then apply. So again, idea is the same to reduce the water table for the clay type of soil. Then when the clay type of soil, you can use electroosmotic method. So again, in the last class also we mentioned that. So we have 2 electrodes and pass the current, different voltage, and then H plus and H minus, water will break up. One will go to anode, one will go to cathode. And then mostly the cathode will be just well points, and you can just pump the water out from the well points. So, obviously in this method, the electric current, so direct current generally you required to, between anode and cathode. And as I mentioned, electrode spacing should be 4 to 5 meters. And the potential difference, obviously, of the electrode kept between 40 to 180 volt. And the placement of electrodes is done in such a way that cause movement of water away from the excavation. So you need to choose this, which one should be anode and which one is the cathode. And then obviously cathode side will be the well point. Okay? And thus thereby increase the shear strength of the soil and the stability of the slopes. This is how it looks like. So you see here, this is to the pump over here. This is the well points is anode, this is cathode, and this is the initial water tables. There should be the voltage difference, and then the water will be going towards the cathode, and then you pump the water out. Okay? So this is how how it looks like. U.S. Army Corps of Engineers, so the well point header, and then well point pump. What is the anode probe and cathode probes? How many you need to do? Several of them, and then put the well point obviously to the pump where the cathode, right? So then the velocity of flow towards the cathode. So it depends on this the equation of Scott, 1968. So you can velocity flow, you can find out K minus IC. K is not the permeability, is the electroosmotic coefficient of permeability, because it's electric gradient. And then also IC is the same like I, it's a hydraulic gradient, change in head loss divided by the distance. Same thing over here. Electric gradient is the electric potentials divided by the distance between these two electrodes, exactly same. And then these will give you what type of, for the water table reductions, depending on the particle size, what method you need to use. So whether you use the pump, submersible pump, whether you should use the well point system. And if it's a clay type of soil, you have seen that you need to use the electroosmotic method or vacuum consolidation method to find out. So to lower the water table. So in general, design of water table required groundwater dewatering required the size of excavation. So is it now what should be the safe and planned dimension and depth? The soil condition, what type of soil is there at the site, permeability of the soil, unconfined compressive strength of the soil, depth of water to be lowered. So depending on the method, the water table reductions, you can use any method. Stage of well points, number of well points or deep wells. So you need to decide that. The spacing of the well points, how many number of well points, what should be the spacing of the well points. And then also you need to know the pump size. And then also the pipe size, how much is the diameter of the header or riser pipe. So all these things you need to decide to lower the water table or dewatering technique. So here, theoretically, the excavation below the water table necessitates some kind of dewatering technique. So again, low permeability soil when the clay is less than 10 to the minus 6 centimeter per second. Do not present much problem with seepage because the discharge is generally small. And then if the more than that, so obviously then the dewatering technique is good. So because the problem is, when you have make a borehole, if the permeability is too low, the water cannot come to the well. So you cannot pump the water out. So its permeability is very low. Field control, although it is expensive, dewatering often becomes necessary to underground construction. So as I mentioned, you are constructing basement or water table is too low, too up. So you need to reduce that, or underlying pipe installation or anything. So that type of situation, you need to do that, although it is expensive. So dewatering process, I'm not going to go in detail over here. As I mentioned, all these methods are there. So you need to see design method. You need to check what type of pump size we already explained. So you can just read that. Summary of dewatering technique again of initial method is sump and pumps and ditches. Then the conventional well points, the vacuum well point, deep well point, and electroosmosis and jet equator well point system. So these are the different system, depending on how much is the capacity you want to reduce the water table reduction. So this is a summary of that and what type of soil is applicable. It's a well point dewatering system. Some of the things you can see over here, these are the header pipe, and then the vertical one is the riser. There are several and it can be connected, and then the main pipe is connected to the pump. Okay, so this is how it looks like. You see the pump is there, huge pump. There is a header pipe, and there is a riser. There are several, and there is different spacing. You can just pump the water out. So design parameters we need to check. The most important thing is height of the groundwater above the base excavation is required, and then also the permeability of the soil over there. So if you make a well, if the permeability is high, then the sand and gravel type of water will go quickly, and then you pump the water out. It's easy well point method. But if the permeability is low, then in that case either use this the vacuum consolidation method, or maybe that, as I mentioned, the electroosmotic method. Okay. So then there are a few things you need to check for every the well points. How much is the area of influence? So this is the equation you can use to calculate. So every well point, how much is the area? So basically, as I mentioned, if you well points, there is a radius of influence. Okay. So how much is the radius of influence? So you can use this equation where Ri is the radius of influence, and then C prime is the for different well, for the single well or for different well points, and then height of the phreatic level. So how much is the initial phreatic level? How much is the drawdown at the end? And then also you need to know how much is the permeability. So now the thing is, it can be arranged in a circular way, or it can be arranged arbitrarily. So and then so what should be how can calculate how much is the discharge? So this is the point P over here. This is that if you know the distance from the different well points, and you can and irregular. So this is the equation you need to use. The first equation. The second one, if the wells are from the pumping well, the point P. So if it is a circular arrangement, then this is the equation you can calculate how much is the discharge. So I'll be solving one problem using this equation. So I'm not going to go in detail here, deep well system. So this will give you some idea. This is from the Mansour and Kaufman's paper. So basically, how much is the size of the pump, minimum size of the well, how much is the maximum capacity of discharge. So all these things you need to decide. So and this will give you a guideline. Okay. And as I mentioned, the design chart, the well point system, this is the clean. I already mentioned this is from the NEVAC system design chart. This is for the clean stratified gravel. Earlier one is stratified gravel. This is earlier was the homogeneous gravel, sand and gravel. And now this is again, as I mentioned, the same table I mentioned over here. So just for example, if you are designing a deep well system and we have a different well point, so we need to know how much is the equivalent area is going to cover. Okay? So, and then from there you can find out how many number of wells required, how much is the total quantity of discharge, and then how many number of well is required to complete this dewatering system. So I'll be solving some problem, maybe one from here. And this one is the cutoff wall. So generally we don't use that just dewatering, not dewatering, so this is total cutoff, the sheet piles, that may be diaphragm walls, there may be solid slurry trenches, the second drill seal sapped walls, tremie seals, permeation grouting, and the ground freezing. So these are is complete cutoff water. Okay. Then I just want to talk about a little bit of that preloading one. Now how to improve the get rid of the water basically, and then how to improve the strength of the clay. There are different methods we need to use. One is the preloading or pre-compressions. Okay, so also I'll be using this method. Do you think I should use first instead of pre-compression? I should talk about consolidation first, and then I'll come back here, or everyone knows consolidation process. I'll go quickly maybe after I explain this pre-compression things. Okay, so preloading is basically, you just put a heap of soil into that particular area, and then the clay is going to settle because permeability is low because it is going to settle. It takes longer time. When the clay is almost settlement is done, then you remove that preload and then put your actual structures. So when you put your actual structures, then there will be a less settlement. There will be no settlements. Okay. So preloading of the soil must include consolidation, which decreases the volume of the voids, resulting in the settlement of the soil surface. And each foot of granular clay deposit, so sometimes the load is coming on the soil is basically 100 pounds per foot square. And sometimes if you put a 30 feet of height of this preload, the foundation load is sometimes 3,000 pounds per foot square. Okay, so it is quite heavy load, and that is suitable for many structures. So that's why people use like a 30 feet and just leave it. Sometimes if the soil is very soft, even 30 foot or 10 feet, just put a soil and then the soil is going to fail. So in that case, you cannot use that the heap of soil. So in that situation, because that heap of load, soil cannot even take that load. So in that case, the vacuum consolidation will be suitable in that situation. So pre-compression, as I mentioned, is simply a place of surcharge fill on the top of the soil that requires consolidation, and just leave it. Once the sufficient consolidation takes place, the fill can remove and construction takes place. Okay? Fill typically 10 to 25 feet thick and produce a settlement to 1 to 3 feet. Okay, most effective in clay type of soil. Again, the consolidation is expulsion of water from the soil sample, so it takes time. So so most of the time, what you do, you need to put a settlement plate or you need to put a pore pressure transducer. So that will tell you when you need to remove the load. So when the pore pressure transducer, meaning it shows the pore pressure is 0, meaning the consolidation is done. Consolidation is expulsion of water from the soil sample. When the consolidation is done, there is no water pressure. So then remove the water table. Also, you can measure the settlement plate, find out the settlement below the heap of the soil. So when the settlement is almost constant and stable, then you just remove that load and do your actual consolidation. So advantage of pre-compression is requires only conventional earth moving equipment, just heap the soil. The only thing is where you are going to heap up soil, that much quantity. So any grading contractor can perform this. Long track record for success is very easy method. Okay, you see the Q1 and Q2, so obviously more load, settlement is done. So then the actual structures is going to undergo less settlement. Disadvantages: surcharge fill must be extended at least 10 meters beyond the perimeter of the plant surface, plant construction. So you have to go a little bit wider. Transport of large quantity of soil is required. Sometimes it is not locally available. This is the point. Then the surcharge must remain in place for months or years. Thus the delay construction. So when the construction is we don't need the construction to be faster. Just delay construction. So then you just wait, keep that load, and then just leave it for some time, and then see the consolidation and do it. So sometimes we don't have time, so we need to do the construction faster. So what I need to do, we need to accelerate the rate of consolidation. So that is the different methods. We're going to talk about that using the vertical drain. So you will be either using sand drain or band drain or PVD. So this is what is happening in the settlement. So when you put a surcharge load, obviously with the time, how the sample is going to settle, and that when the final settlement is even more than the design settlement, so that is easy to design your structures. Okay, because whatever the design settlement you are expecting, the settlement after you put your structures is already settled that much. So it's very easy. It's not going to settle anymore. So this is the again the surcharge load for the clay sample over here, and what is happening. So we have that the surcharge load and the final load. You know how much. So then we can find out how much is this the total pressure, pre-concentration pressure. How much is the pressure plus surcharge pressure. So most of the time this is easily you can find out that under the surcharge load. How much is the degree of concentration? So again, you need to go back to the concentration. So what type of clay is there, whether it is normally concentrated clay, whether it's over-concentrated clay, and how much the load you are applying. So whether it is more than pre-concentration pressure or less than pre-concentration pressure. So easily you can calculate the settlement. There are different graphs are available, so you can easily find out from here to this graph. And you can find out also from the degree of concentration. Again, degree of concentration is how much is the ultimate concentration compared to the current state of concentration. So easily you can calculate that. So from using this equation. Okay? So I'll be solving one problem also using this equation in pre-compression. So again, you need to go back to the time factor and degree of concentration. So degree of concentration and time factor, there are several relations there. Depending on the degree of concentration and time factor. Then, as I mentioned, that when there are situations when you don't have the pre-concentration pre-load, you don't have enough soil available at the site. So what you need to do the vacuum preloading. So vacuum preloading, so using atmospheric pressure and apply vacuum, and then no need to add heap of soil. So that is the advantage of using this. Okay? So and this method is first introduced by Zellman from German, the German guy, and he utilizes atmospheric pressure to the preload soil. It consists of vertical drain, it consists of horizontal drain, it consists of drainage layer, impervious membrane, and peripheral trenches, and the vacuum pump. So obviously, when you apply vacuum, we need to put that on the top surface. Should be completely sealed, and then apply vacuum and then atmospheric pressure, and then there should be the peripheral trenches, and then again you pump the water out basically. And obviously there is a isotropic concentration, so vacuum drains. So obviously most of the time idea of using this vertical drain is most of the time when you apply load for a clay type of soil, the water will go on the vertical directions. But if you use the vertical drain, the water can go in the radial direction also in addition to the vertical drain, and thus increase the rate of consolidation. So this is the idea of using vacuum preloading. So what is happening over here in the preload, this is what is the difference between this field preload and the vacuum preload. Field preload is you have to put a heap of soil, correct? So we need this much of quantity of soil. The vacuum preload, you see there is no soil, only thing is you have a sand layer and a little bit of the barrier material to seal it, and then using this atmospheric pressure. And then also there is a trench over here, and then with the membrane, the vacuum preloading is going to occur. Okay? So these are different things. I'm not going to go in detail over here. You can read this. And then the common advantages of vacuum preloading is no extra, as I mentioned, so no extra fill material is needed. Construction times are generally shorter. It requires no heavy machinery. It doesn't require chemical admixtures. Okay, we will talk about more the chemical admixture things later on. So further advantages of this is isotropic consolidation. Again, we are using that eliminate the risk of failure under additional loading to the permanent structures. There is no risk of slope instability beyond the boundaries. Obviously, most of the cases when you use the fill material, sometimes the load is too much. Even that preload soil cannot take if the soil is very soft. Okay? And it allows control rate and magnitude of loading and settlement. Okay. These are the few advantages. And the problem associated with vacuum preloading, obviously there are every method some advantages and disadvantages. To maintain the effective draining system under membrane that expels water, air throughout the whole pumping duration, it is difficult. Keeping a non-water saturated medium below the membrane, also, it is difficult. Maintaining an effective level of vacuum. So again, you need to be properly sealed. Maintain the leak-proof system, in particular to pumps or membrane connections. Anchoring and sealing of the system at the periphery, also where the pump is, peripheral drain is there. So we need to, anchoring is required. And then also reducing the lateral seepage towards the vacuum area. So theoretically, it apply around 100 kPa, but practically is 60 to 80 kPa. Okay. So there can be a lateral steep drain also, using that lateral steep drain. So to remove the water. So again, this is the example of, as I mentioned, the vacuum and preloading. So obviously over here, we can use both, use the field load plus the vacuum. So over here, you see the vacuum, there is a geotextile, so geomembrane over here, and apply vacuum over there. So we can combine these two methods together, and then also the vertical drain to remove the water. This is again, suitability of preloading. It depends on the cost effective, depending on situations. So vertical drain can be used shorten or time preloading. Typically install a depth of 30 meter, vertical depth more than 60 meters or more than 60 meter in some project. Preloading is effective when the loading is higher than the soil preconstituent state. So again, as I mentioned, sometimes even preload, the soil is very soft, it cannot take even the preload. Okay. So this is installation of the sand blanket and the vertical drains. So we'll talk more in the PVD one, but this is the PVD, the vertical drain you can use. I'm just going to go in detail. Seal the membrane, how we can install that monitoring instrument, all this stuff, the vacuum and surcharge. So again, I just want to tell a little bit of this. So here you can see for 3 different situations. This is like figure B is the conventional surcharge. So basically what is happening into that, the total vertical stress, effective vertical stress, and water pressure. So what is happening over here? And then, so over here, initial conditions, you see the total vertical pressure and water pressures. So again, you need to understand that. So the pore water pressure is EU generally, and then the effective stress is total vertical stress minus the water pressure. So the more effective stress is more, meaning it can take more load, right? So in terms of over here, in terms of vacuum-induced surcharge, you see the water pressure is negative. Okay, the water pressure is negative, so that is good basically. So water pressure is more means what? So the effective stress will be less. So in the soil mechanics, you need to understand that the effective stress is more. Effective stress is the water pressure is more is not good. Okay, the soil, for any type of soil strength is coming from what? For granular type of soil, the friction between the particles, right? Friction between the particles. More friction means more strength. That is for the granular type of sandy type soil. For clay, more strength is made more stickiness, correct? More cohesion. So now the thing is, pore pressure increase, meaning what? So you assume there is a soil particles, another soil particle. The pore pressure means water filled inside the voids of the pore space, right? So now pore pressure increase means what? Water pressure will try to separate these particles. So basically, instead of friction or instead of increasing the strain, is to separate the particles. So suddenly the soil loses its strain. So that's why during the earthquake, what happens? The pore pressure increases. Suddenly, soil loses its strain because there is no contact between the soil particles, and then soil collapse, okay, or foundation collapse. So over here, in case of vacuum surcharge, the total vertical stress remain unchanged, and then the increase in the effective stress due to reduction of the water pressure, and that is the applying negative pressure. Okay, and in case of conventional surcharge, the total stress will increase due to additional load. Okay, thus the effective stress will also increase as well, while the water pressure remains unchanged. Okay, so this is the conventional surcharge and the vacuum surcharge. Vacuum preloading, as I mentioned, these are the different things. These pictures have taken from basically, GIAN's book, but mostly I visited in Shanghai, China. So there we really observed all this stuff, how they install this PVD, installation of the drainage tubes. It's a huge area, and then the vacuum pump. So all this, basically the PVD, and they are not using sand drain, but using this PVD, and then geotextiles, and then also the vacuum preloading. All these things they use in this area. The PVD rigs. It's very, the water surcharge sometimes is very, is difficult. So here of the project, this one, in Shanghai, as I mentioned, so it's a huge area. So most of the time, what they did over here in this project, so they the dredging material from the sea, and they are just the pump. Ideally, it should be sand, but they pump the clay, and then the slurry and clay water, and then they want to do the construction on that type of area. So we have to do the PVD, we have to do the vacuum pre-consolidation. So you cannot apply the huge surcharge load on the top of the soil because it cannot take that load. So that's they use the PVD and the vacuum consolidation to consolidate the area. Okay. So this is the area, planned area, as I mentioned. So this is how the water is coming out using this PVD and surcharge load and using vacuum. This is a huge area, it looks like. So these are the different pumps you see, and then also the below there is a vacuum geomembrane, and then a little bit of surcharge. And then also this is how it looks like, the vacuum preloading, and also what is the connections, and then also you see the large vacuum pump to release the water. This is the vacuum preloading. We'll be talking about more in detail. So basically the PVD is basically there is a high density polyethylene type of material at the core, and on the top there is a geosynthetic material, and then so that only the water can pass through, and then it will no soil can pass through that. Okay, and then it will go the vertical directions. Okay, so that is the idea of vertical preloading. So these are different connections they used, and then top is the PVD, how they're connected. So this is the old one. Earlier they used the older system. Now have a newer system like that. They used more efficient in connection a few drains and tubes. I mean, it is not easy. It's a very simple process, but a huge area, and then installation of PVD, and then connecting it, and then apply vacuum pressure. That is a bit challenging because the soil is so soft. Okay. Then the vacuum preloading also, as I mentioned over here, this is how it looks like. And then over here, this is the how obviously when the consolidation is done, then you need to check how the strength increased. Then you need to do some tests at the site, and then you can determine how much the strength has been improved. Okay. So these are mostly the vacuum preloading and then PVD stuff. Okay. This is another air injection hose. Sometimes you use for the test section, vacuum preloading. It's much more detailed, but I'm not going to go in details over here. And then the electroosmotic I mentioned already, vacuum preloading. Also, they use that electric current, and easily you can calculate that. I'm not again. So they use that electroosmosis, but they use the electrokinetic. They use the electrokinetic geosynthetic material. So geosynthetic is there is an electric piezoelectric piezometer are installed, the conductive polymer. So conductive polymer is installed in the PVD itself. So and then the electro. So basically, you can say this one is electroconductive electroosmosis with this conductive polymer. Okay, so we call it EKG. A little bit different electroosmosis method. This is how they do at the site. The vacuum preloading, including this one, electrokinetic geomembrane. So, and then the connection between the pipe and the geomembrane. So the PVD, how they're connected to the vacuum tube, and then next to PVD. So all these three connections are there. How it looks like, the drainage tubes. A lot of pictures. Again, these are the pictures from the Shanghai, China. This is how they install the membranes. This is a huge area. So how the installation of the membrane. So it should be impermeable membrane, so that it apply vacuum. This is how it looks like, the overall, and then the perimeter trenches, and then you can just use the pump to get rid of the water. Okay. This is how it looks like, the settlement with time. You need to use that, as I mentioned, so like the sensor is attached to that or kinetic in geomembrane. So, and then find out that they compared with the normal one, and then also use different types of the piezoelectric with the sensor. Okay. And then they mentioned that although these sensors is very recently new, so people are, and they proved that, okay, this is much better. The settlement is much better than the conventional one. Okay. So I just, any questions from this? So we have how much time? So
Sir, just a minute. Actually, I just request you to the first slide of vacuum preloading. So can you explain that? The first slide of vacuum preloading.
First slide.
In which the entire process is there's a schematic diagram.
Okay.
That in which it's clearly shown the trenches, etc. I guess it is slide number 62 or 63. I guess
62.
I think so. I'm not sure.
One?
Yes, this one. Yes, sir, this one.
Yes. This is the schematic diagram, but the pictures you have seen in the Shanghai, as I mentioned. So no, this is it is difficult to control. I mean, it seems like, okay, you apply the vacuum, you apply the sealing, even the sealing using geomembrane, and then how to anchor at the peripheral side on the side. It is not easy job. You need to losing the vacuum. And then also the clogging, and then PVD. So a lot of things. So what is the question?
So actually, this vacuum, how actually this was what I was a bit how they are able to maintain that vacuum in this particular.
That's the one. You cannot maintain that. It is difficult. As I mentioned. So when I visited the Shanghai, in the side there is a constant, continuously they are monitoring, and then obviously they will be losing some. Every time it is difficult to maintain the vacuum pressure, and because it depends on how you seal it. And then sometimes the laying of geomembrane, sometimes, if there is any leak in geomembrane while in a huge area, it is very difficult. And sometimes you have to anchor it, right? And then also how they are, you have seen a lot of connections, the PVD, and then in like a riser pipe or header pipe, that type of connections, there are different types. And then there are multiple of these, So it is not easy task, but, and these pictures is basically that ideal situation, but in real life it is different. I mean, if you see that the pictures, all this, the picture I've shown, that one again, it is not easy. On the site itself, I have seen there are 2-3 site office, and all the time they are monitoring the pump capacity of the pump, which one is even for the construction site, they have huge generator. There is no electric supply there. So all this time is a very expensive process. And as I mentioned, and then also, as I mentioned, because they use vacuum, because the soil is so soft, you cannot put a heap of soil and then keep it for some time. It's going to fail. Yeah.
Okay. Thank you so much, sir. Thank you so much.
All right. So any other question? So this is most of the notes I've taken from this GIAN's book. and some other books also. All right, so if it is not no questions, then I can just continue again. The next topic is, yes. Okay. Again, if it is normally, when we cannot use the well point method, right? So when this is pure clay, and if there is no choice, so then you can use it. You can use that. Also, sometimes electrokinetic method, the same thing you can use for not only dewatering. So you can use that method basically for the removal of contaminant from the clay soil also. Okay. So again, when the other method is not suitable, like a well point is easy, or when you then you can use that. Then obviously we need to have the electric gradient, right? So you need to pass the voltage and direct current, and then you have to have that well point system. One will go to cathode, one will go to anode. Okay. Does it make sense? So generally we don't use that, but if it is, we need to. And if it's a pure clay, permeability is really low. The water cannot flow at its own. So in that situation. All right. Okay.
So I just want to understand these PVDs, prefabricated vertical drains. Is there any specific design for
yes.
different
I'm going to
types?
talk about. I'm going to talk about that in the next section, the PVD and the sand drain. I will talk about that. And
Okay. Yeah. Thanks.
Okay. So now the next topic is the consolidation. Do you think that I should explain the consolidation, or I just go quickly? Just to quick refresh, or whatever you say.
So better refresh, sir.
Okay. So
But if time permits, of course.
Yeah, I'll just go quickly because I know everyone knows consolidation. Just to go quickly, and then can you see now?
Yes, sir, it's visible.
So what you can see?
This Tarjagi 1D consolidation theory slide.
Okay. Again, you can see now consolidation, correct?
Yes, sir, you can put it in the full screen mode. It is in the slide mode at the moment.
Oh, really? I put
Yes.
it in full screen mode. I can see full screen here. Maybe is it? Can I don't know whether the other slide is still there or not. Oh, okay. So I think I just stopped share then. Okay, just a minute. Sorry about that. What can you see now?
Yeah, it's okay now, sir. Yeah, this is the consolidation page is open.
Okay. So consolidation, again, I'm not going to go in detail. So this is because this topic is mentioned consolidation of soft soil. So consolidation of clay is basically consolidation and expulsion of water from the soil sample. So when you apply load, what is happening in the saturated soil? So all the load is taken by the water, and then you transfer to the soil, and then you need to keep it. It is a time-dependent phenomena, and then it is not quick, because the probability is low. And so obviously, I'm not going in details over here. So obviously, the change in shape, distortion, and compressions, all this stuff. Okay. So sometimes when I'm not going to go in details. So when you do the consolidation, so basically, you need to, on the consolidation test, you can find out the different parameters to find out the settlement idea. The idea of how to calculate the settlement, right? So we can find out the immediate settlement, primary consolidation settlement, and secondary consolidation settlement. So granular soil, what is happening immediately? The soil is really settlement is immediate. But it's a clay type soil that with time the settlement is, it takes time, and then settlement is going to take place. Again, you need to go that what is the pore pressure. I'm going to go here. So what is happening over here for any consolidation, just for example, at certain point, if you apply a load, the pore pressure is decreasing and the effective stress is increasing over here. So you see the effective stress increase when it can take more load. So as I mentioned, the consolidation is the expulsion of water from the soil samples. So this is the skiing analogy you know already, so I'm not going to go in detail. So most of the time, if it's a clay soil is there, so if you apply load, you need to find out how much is the settlement of the clay layer. So it depends on the permeability of the clay, and you need to know the properties of the consolidation test. So from there, you can find out the MV, you can find out AV, you can find out CV, you can find out compression index. From there, you can find out the settlement, basically. So again, this is what is happening over there with time, the total stress, initial time at no time, all the load is taken by this pore water, and then with time, all the pore water is gone. The effective stress is equal to 0, at time is equal to 0. Then what is happening over here? So basically, it's a clay layer. The clay is sandwiched between two sand layers. Load is coming. So total stress, pore pressure is decreasing, and then the effective stress is total stress minus pore pressure. It looks like this. Okay. So at the center is different, and at the side is different, right? The effective stress. So most of the cases, sometimes we assume uniform. Sometimes we assume that when the load is coming, it is like a not triangular, but like a more on the top and then a lower at the ground at the bottom part. Okay. This is at time is equal to infinite. So obviously the total stress and the pore pressure, all the pore has gone out, and then the effective stress is equal to total stress. Okay. So so this is one-dimensional consolidation. So obviously most of the time when you do consolidation is one-dimensional. So basically when water is going only in the vertical direction. This is the Jage's theory. And then in real life, you don't know what type of soil is there. So, if there is a clay layer and there is a sand layer, at bottom there is a gravel or impermeable rock. So water can go only in the vertical directions. So this is one-way drainage. If there is a clay layer and there is a top layers, impermeable sand or gravel at the bottom and top. So then when the apply load, the water can go on the both directions. So that is basically, you can easily calculate the one-way or two-way drainage. And the average strain you can calculate. So again, how much is the height of the soils, how much is the strain, the change in height divided by original height. And there are relations with that, with the void ratio. You can calculate the settlements, from there. I'm just going to go. So here, this is the relation. So change in height by original height, change in void ratio by 1 plus E naught. So if you know how much is the settlement, consolidation settlement, you can easily calculate. If you know the original thickness of the clay, if you know with the application of the load, how much is the change in the void ratio, you can get it from the E log P graph. And then if you know the initial void ratio is that, so you can easily calculate. There are several equations you can use to calculate. So from this consolidation test, you can find out the coefficient of compressibility, that is change in the void ratio by changing the pressure. So again, when you increase the pressure, void ratio is decreasing. That's why the change in the pressure void ratio is negative. Then coefficient of volume compressibility. So we can calculate. So then you can find coefficient volume compressibility is change in volumetric strain divided by how much is the change in the pressure. So you can calculate that volume compressibility from there. Then Jage's theory again. There are some assumptions made in Jage's theory that the soil is 100% saturated, should be homogeneous, Darcy's law valids, all this assumption made. Soil and grains are incompressible. That is not true. Then compression or flow rate, all these things you need to know the assumption made. And the sample is laterally confined, but that is also not true in real life, because in the lab test, the sample is laterally confined. So the consolidation test, again, I'm not going to go in details. It's a circular ring, and then you apply a load. So the load increment ratio is 1. So when you put a load, any load, so just for example, 1 kg per centimeter square, just leave it there for 24 hours, and then take the reading with time versus settlement. And then you go next day, you increase the load, just double. If it is 1 kg, then you put 2 kg per centimeter square, and then take the reading again. And then next day you come, so you just go up to, just increase the load increment ratio as a double, and then keep it for 7 days or 8 days, and then the loading and then unloading. Then from there, ultimately you will get a graph like a E-log P graph. And then from the E-log P graph, you can find out the slope of this line. That is the so there are two types, again, consolidations. So one is the fixed ring, another is the floating ring. So most of the time in consolidation, we use the fixed ring method, the bottom one. Sometimes you can use the floating ring also. So normally consolidated clays, again, the consolidation of clay when you talk about, so we need to know what is normally consolidated clay, what is over consolidated clay. Normally consolidated clay is the clay, the soil has never experienced the stress more than the current stress. Over-consolidated clay is the soil has already experienced the stress more than the current stress. The behavior will be different. And then the settlement equation, so is also will be different. So this is like a E-log P graph. So it is a loading and then unloading and then again reloading. So this is how it looks like. This is the graph you can find out from pre-consolidation pressure. So from the E-log P graph, you can draw a horizontal line at the maximum point of curvature, draw a tangent from the bottom, and then you see the tangent from A, and then make this angle. You divide that angle, and then draw a tangent from the bottom part, and then see what is that pressure. That is the pre-consolidation pressure. That's why you can easily find out. That's why the soil has memory, so it can really find out how much is the stress history it was there, how much is the soil stress. So I'm not going to go in detail here. There are different relations between this compression index and recompression index. So there are several relations that are available. So we can find out for the normally consolidation pressure. So here, if you slope up that line is the compression index. This is decompression index or swelling index. There are several relations that are available. As I mentioned, pre-consolidation pressure. So I'm not going to go here. There are over-consolidation ratio. Also, you need to know how much is the pre-consolidation pressure divided by how much is the initial stress. So you can easily find out from there how much the soil is over-consolidated. Most of the time, the over-consolidation ratio is 1. So meaning that soil is normally consolidated soil. And the settlement calculation, this is the most important. Then later on, we'll talk about that. The settlement. So settlement, you can, if you know the MV, that is the volume coefficient of volume compressibility, then you know the pressure change. You know the height of the clay. You can find the settlement. You can calculate from the change in void ratio by original void ratio, and if you know the height, then you can calculate the settlement. There are 3 types of the settlement you can calculate. The compression index, you can calculate from there, the slope of these virgin compression lines. And there are some relation, as I mentioned, the compression index. There are some relations are there with that recompression index or swelling index with the compression index. When the data is not available, you can use this. And this is the settlement calculations when you have the pre-consolidation pressure and additional load is more than pre-consolidation pressure, so we can use this. So just behave like a normally consolidated clay. This is delta S is equal to Cc times H by 1 plus C naught. Initial pressure P naught, how much is the change in pressure divided by P naught. Change in pressure is you can calculate using several methods. Either use 2:1 method or Boussinesq equation or equivalent point method, or you can use M&M method or M1N method or Newmax chart. So there are several methods to calculate how much the additional load is coming because of this additional surcharge load. And then you can find out the settlement. So this is normally consolidated clay. If it is highly over-consolidated clay, equation is same. Only the Cc is now replaced with Cr. And then if the some the soil is slightly over concentrated clay, then you can use this equation over here at the bottom. So there, the pre-concentration pressure is important there. You need to use that. So this is all the equation as I mentioned, depending on the initial stress and pre-concentration pressures. This is the pre-concentration pressure, so you can use the settlement equations depending on when the pre-concentration pressure is more than the with the surcharge load. So all three equations can be used to calculate the settlement. Okay. I'm not going to go in detail over here. And then again, for the conservation theory, so this is the theoretical equation of this conservation, du by dt. The change in the water pressure with time is equal to how much is the coefficient of consolidation, and du by dt, that is the d square u by dj square. Okay. So the CV is the coefficient of consolidation. CV is equal to K divided by MV by gamma W. Again, you can easily calculate that CV. And there are several, how to calculate the CV. There are two methods, again, the Casagrande method and Taylor's method. So, and there are relations also between U and time, that the time period. So I'm just going to go just one case over here. This Casagrande method, you can calculate how much the value of CV over here. So CV is equal to 0.197. How much is the degree of drainage? Only thing is the degree of drainage is depending on what type of, is one-way or two-way. And then another method is the square root of time, is the Taylor's method. So we can calculate. So here you can find out how much is the D90. So 90% consolidation, CV is equal to 0.848, height of drainage times T90. So you can easily calculate that. And then also other method, there are early stage method, hyperbola method. So you can use that also for how to find out the CV. Okay, I think so for the settlement, you can calculate elastic settlement, primary concentration settlement. In real life, you will not get your clay. If you have granular type of soil, you can calculate for the elastic settlement method. There is several equations you can use, and then you can use for primary concentration settlement. You can use for secondary concentration settlement or creep, or if there is highly organic soil, you can use the tertiary concentration also to find out the total settlement. So anyway, so this is, I just go very quick about this consolidation. Okay. So I'm just, I just want to stop this sharing this, and then I'm just going to share that. Vertical drain practice, just a minute. Okay, you think that, okay. And so that will be easy even. So after what time I should do that actually? It's 9:50, right? Yeah. Half an hour. So what do you think? I mean, whatever this one, I don't know, this is just a lightning method. I just talk about because I know everyone knows the consolidation, but I want to explain that the PVD and sand drain, and then I'm going to solve some problem also, the PVD and sand drain. Do you think that we need some break now? And then I'll continue with that, the theory, and then at the same time, we'll be solving problem. What do you think? Okay. So how much break do you think I should? It's like 15 minutes. Okay. So after 15 minutes, I'll join. I will go to that little bit slow on this the sand drain and band drain, PVD, and then I'll solve some problem. Okay. All right. Thank you. Okay. And then this will continue up to what time?
Recording in progress.
So this will following this tutorial, correct? Oh, okay. Okay. So that then will be done. Okay. But yeah, I'm going to cover first the vertical drain, and then I'll start. So can you see the slide now? All right. Again, welcome back. So the last session, consolidation, was a lightning session, correct? So I know everyone knows, but just quickly because it is in the syllabus. So now consolidation. So basically, consolidation test is very important. You can find out, do simple consolidation test, but you can find out so many parameters. Okay, you can AV, MV, CV, degree of consolidation, and then you can find the settlement. And then it depends on what type of clay you are using. So now, as I mentioned earlier, the consolidation, the clay permeability of the clay soil is very low. So consolidation it takes time, it's time-dependent phenomena, and it is suitable for only for granular clay type of soil, because the consolidation is expulsion of water from the soil sample, correct? So now I'm going to talk about the method of providing vertical drains. So there are three methods you can use so that the consolidation, the rate of consolidation can be faster. Right? Just so that rate of consolidation can be faster. This method, the vertical drains pour water squeezed out during the consolidation of clay due to hydraulic gradient created by the preloading. Okay, so the preload, as I mentioned, water can flow a lot faster in the horizontal directions to the drain and flow freely along the vertical drains. So that is how generally used. Consolidation is, Terzaghi's theory is a one-dimensional consolidation. This the water can flow on the vertical directions, but in real life it can flow horizontal or verticals. So if you create a vertical drain, the water can flow in the horizontal directions and go. That is rate of is consolidation will be much faster. Thus, the installation of the vertical drains in clay reduces the length of the drainage path and thereby reduces the time to complete the consolidation process. So there are three types of vertical drain. One is a cylindrical sand drain, and then geosynthetic or fabric encased sand drain. The sand drain, but you have to encased with geosynthetic or fabric encased. And last one is the prefabricated vertical drain. Okay, so this is the situation like the consolidation without drain and with vertical drain. So normal consolidation, so most of the cases we have that thick layer of clay, we have a surcharge load, just for example, and then we have a sand layer, so the water can go both sides, and then just only in the vertical direction. But when you put the vertical drain, so then water go in the horizontal direction also, and then go vertical, so horizontal and vertical. Okay, so that's how it's much faster. So as I mentioned, the first thing is the sand drain. The sand drain, basically what you do in the clay soil, just make a borehole and fill it with sand, and then apply a little bit of surcharge load on the top. And then top layer also the thin layer of sand, so that when you compress this, from the water will come out from the clay and then go in the horizontal directions to the sand and then go up vertically and then releases from the horizontal. So on the top layer. So basically, advantage of sand drain is sand drain provides an easier path for the excess water to flow as it's squeezed out of the layer of soil during consolidation. It increases the rate of consolidation settlement, consequently acceleration of the rate of gain of shear strength, obviously, and then reduction in the lateral transmission of the excess hydrostatic pressure. So amount of time takes, as I'm telling you, the time takes, the consolidation can reduce as a fraction of that in vertical flow only. So we have earlier normal consolidation vertical flow and the radial or the vertical combined. So the sand rain used to conjunction of the dewatering system to lower the groundwater table in the stratified soil. Sometimes you have a clay layer, and if you put a sand layer, so basically the the water can go into the sand layer, and then you can use that also for in the dewatering system. So this is how it looks like, the sand rain. So you see here the surcharge load, and there is a clay layer over here, and then the top layer is the sand, and there is a water table is there also. So what is happening here, the sand layer at the top and bottom. So obviously, if you put a surcharge low, water can go. Height of the clay layer is HC. It's a sand rain, and then the water can go in the radial directions. Here, the sand rain radius is RW, and then what is happening over here in the plan, you see the blue dot is the sand rain, and this is the equivalent diameter of this. Equivalent diameter, D is the equivalent diameter that we need to calculate, and depending on the pattern. So this is like a triangular pattern. You see here, this is the triangle. So this is a triangular pattern, but you can find out the equivalent diameter. So for one sand rain, how much is the area is going to cover? Okay, so when you're designing a particular area, so to accelerate the consolidation process, you need to design like how many number of sand grains you need to put. Obviously, what should be the diameter of the sand grain, what should be the depth, that is a different thing. But again, you need to know how much is the area, the effective area you need to calculate the effective area. So over here, the second schematic of a sand rain, over here, this is the equivalent diameter, DE, as I mentioned. It's a clay layer. And then in the middle, this is sand. But sometimes you see in the junction between the clay and sand, there are some clay and sand mixed together. Okay? So permeability of the sand is much higher than the permeability of the clay. So what happened is mixed together. That portion is called the smeared zone. The mixed zone is the permeability is much less than the sand. Okay, so when that's obviously you cannot avoid that when you put a sand rain. So you use it most of the time in the clay layer. You put a mandrel steel pipe and then put sand, and then you take out the steel pipe, and there is a column of sand, right? So sometimes obviously there is a junction. There will be a mixture of this sand, and this is a smear zone. So what you need to do basically after backfilling the drill hole into the sand, a surcharge load is applied on the top ground. Surcharge load increase the pore water pressure in the clay, and then excess pore water clay dissipate, draining this both vertically and the radial. So radial direction and go vertical. So that's how the consolidation is faster. So there are a few equations in the consolidation equations over here when the flow is in the radial direction. The flow is the radial direction. While talking about the consolidation, their degree of consolidation is U, that is in vertical direction. Okay, generally you don't write that because the exact theory is one-dimensional consolidation in vertical directions. But when you put the radial directions, the meaning is in we just write UR, and the equation is 1 minus e to the power minus 8 TR by M, where TR is the same. TR is the time factor. Whatever you studied, whatever in the consolidation, TR, it is depending on the degree of consolidation. And so T is equal to earlier one, it was the same thing over here. The TR is equal to here CVR times divided by DE, that is the equivalent radius. Okay. So sorry, equivalent diameter. So here, only thing is the CV, earlier one, the normal consolidations, CV generally is the vertical consolidation. We generally don't write CVV, but here you see the CV suffix R, that is for the radial directions, and T is the time, and DE is the equivalent diameter, depending on the arrangement of this. So there is an equation for that. You can calculate how much is the equivalent diameter. And if you know that CV, you can find out CV, you can also calculate from that K is equal to CV MV gamma W from there also. From the permeability, you can find out K is equal to permeability of the clay is equal to, indirectly, you can find out from the consolidation test results, K is equal to CV MV gamma W. that same way you can calculate that CV in radial directions, K, but here the K is in the horizontal direction, permeability. And then you can write these equations, delta E, mv is equal to change in void divided by, 1 plus, change in pressure plus 1 plus E, the vertical. This is the vertical void ratio. And then gamma W. So here, only thing is, in normal consideration, difference is normal consideration. We don't talk about the verticals. We generally don't denote or tell that this is the verticals. Everyone knows this is vertical. Only thing is when the radial one or horizontal one, we just write R. Okay? So here, at the degree of consideration, here R, you see the minus 1 minus e to the power minus t 8 times t by m. But m is given by this equation, n squared divided by n squared s, this equation, where n is how many, n is equal to, you can calculate dE, that is the equivalent diameter, and 2 times Rw is the radius of the well, radius of the sand well, okay? And S, you can calculate Rs by Rw. So also you can calculate that Rs by Rw. Where Rs is the radial distance from the center of the sand grain to the farthest point to the smeared zone. Okay. So again, as I mentioned, this is some portion is mixed, the smeared zone. So that's the farthest point, you can calculate that. So again, as I mentioned, that the PVD can be sand grain can be square pattern, it can be triangular pattern. So how it looks like, earlier one you have seen the triangular one. And then you can find out that the spacing between these two sand grain, and then you can find out the equivalent also. So you can, how much is the influence zone of the drain? You can calculate using this equation, depending on the pattern. So if it is a square pattern, it is 0.546 times S. S is the drain spacing. And if it is a triangular pattern, it is 0.525 times S. S is again the drain spacing. So how much is the spacing between one drain to another drain? It's center to center spacing. This is how it looks like on the sand drain. So we have impermeable bed here, and then the spacing between these two sand drain, and then there is a filler bed on the top, and then the embankment. So obviously, you can see here how the water is going in the horizontal directions and then go up. Okay? So every sand drain, you see the plan over here. Every sand drain, there is water is coming in the horizontal directions, and then you need to find out how much is that radius of influence. Okay, how much is the radius of influence? That one you need to calculate. So during the installation of the sand drain, the zone around the, so as a smear zone, we mentioned the periphery, around the periphery of the well get disturbed, and the horizontal permeability is in the disturbed zone gets reduced because it is mixed with clay and sand, right? And this effect is called the smear zone. Impede the flow towards the well, so that really hinders the flow. Okay. So what are the general features of the sand drain? So diameter of the sand drain generally varied, should not be less than 30 centimeter. Should not be less than 30 centimeter. Placed in the square pattern, and the spacing is placed in square grid pattern. It can be triangular also. Spacing is 2 to 3 meters between each drain. Depth of vertical drains should extend up to the thickness of the compressible strata. So you need to know how much is the depth, of clay layer you want to reduce. You need to go up to that depth. Okay? Horizontal blanket is placed at the free draining surface on the top of the strata, and then you put a surcharge load. So basically, water can go horizontal, water go vertical, water go horizontal and then vertical, and then on the side, water can go, and then So the horizontal, and that may go up to 1 meter, the horizontal blanket on the top. Soil surcharge is in the form of embankment, is constructed on the top of the sand blanket in stages. So these are the different, the vertical drains, different installation method. Idea is basically you need to place soil, you need to use a mandrel, just put a steel pipe, and then take out the pipe, and then fill it with sand, and then take out the pipe. Okay. So there are different diameter, different spacing, different length, and then so how this is the sand drain is installed at the site. We're going to go in detail here. Some disadvantages of sand drain is to receive adequate drainage properties. Sand has to carefully chosen. It might be seldomly found, so we need to find that close to the construction site, right? Drain must be discontinued because of careless installation of horizontal drain placement during the construction process. During filling, bulking of sand might appear. That would lead to the cavities and the subsequent collapse due to flooding. So that also need to check. Construction problem and budgetary burden might arise due to the large diameter of the sand drain. So we cannot use that. Disturbance of the sand soil surrounding each drain cause installation may reduce the permeability. Again, as I mentioned, the smear zone is going to occur. And then also, because the sand drain, sand is also steep material, correct? So sometimes, when you do apply load, it is acting as a sand column. So we don't want that. We want to compress the clay, right? So sometimes it reduces the effectiveness of the preloading of the soil because of the reinforcing effect of the sand. Again, as I mentioned, so when you do the degree of consolidation, overall rate of consolidation, we need to consider how much is the vertical consolidation, how much is the radial consolidation or horizontal consolidation. So du by dt, normally du by dt, that change in pore water pressure with time is equal to Cv times du by du square u by dz square. So this is the equation. So because of radial drainage, so the first part is added, CH, that is CH is the horizontal coefficient of consolidation in horizontal direction, the radial directions, and then this part is coming into picture. Okay, so this is the equation, differential equation for the consolidation. So and then overall consolidation, you can use these equations where 1 minus u vertical times 1 minus u radial. Okay, so we'll be solving some problems using this equation. For PVD, so again, we have PVD is like a, again, this is like a vertical, inside there is a core, and then the top, there is, if you take a pipe and then just flat it, just press it. So that is like a PVD, prefabricated vertical drain. So there, so I can show you some figure there later on. So here the concept is the same. So inside there is a core. And there are different patterns inside, and then there is a high density polyethylene type of material. And then on the top portion is covered with geosynthetic type material. So that when the water will go through the geosynthetic material, so only the water can come. So no soil particles. And it comes in a roll, so it is easy to install compared to the sand drain. That's the advantage. We will talk about that. So then also you need to find out here the equivalent diameter. Although it is a flat, with certain width and thickness, but we need to, when you calculate like earlier one, the sand drain, you need to find out how much is the equivalent diameter is going to cover because of the sand drain. So, and then the equation is a little bit different than over here in the earlier one. So again, equivalent diameter, so is equivalent diameter 1.06 times S for the triangular pattern, 1.13 times of S is also for the square pattern. And S is the center-to-center spacing between the drain. And then also you can calculate a similar type of equation, degree of consolidation, but again in the horizontal directions. And then also mu over here, the mu is coming into picture where you can calculate the mu is equal to given by this equation. There are a few things you need to consider based on this figure. TS is the dW, including the smear zone. D is the total diameter. So all this thing equivalent diameter. dW is the equivalent drain diameter. ds is the diameter of the smear zone. Kh is the coefficient of horizontal permeability. Ks is the coefficient of smeared soil. So all these things, based on these values, you can easily calculate how much is the discharge capacity or dW. So if you know the discharge capacity, then you can calculate how many PVD you need to install. Okay. It's a little bit, looks like a little bit complicated, but it's very easy. So depending on, you need to find out the equivalent diameter. You need to find out what type of pattern you need to use. And then use this equation, degree of consolidation. So degree of consolidation, how much they're going to current consolidation time compared to the final one. So you easily can calculate that. So what is the advantage of PVD, a prefabricated vertical drain of a sand drain? The installation of PVD is faster than the sand drain because it comes in a roll, and which results in the lower project cost. Okay. No risk of PVD breaking during installation. So that is, the sand drain can heap discontinuities if mandrel is withdrawn too fast. Okay. Mandrel is a steel pipe, right? So when the PVD breaks, no risk of breaking of PVD because it is a PVD is inside like a prefabricated vertical drain, and then also there is a geosynthetic installed. So no risk of shear failure of PVD during settlement. Sand drains are vulnerable to shear failure during settlement. So again, that is another problem. PVD have for the sand drain. PVD have high discharge capacities, typically 3 to 10 to the power minus 6 meter cube per second to 90 times 10 to the power minus 6 meter cube per second, compared to the diameter of the sand drain. If the sand drain is diameter is 0.35 meter, then discharge is 20 times 10 to the power minus 6 meter cube per second. So it's much less the discharge compared to the PVD. So when installed with PVD, design mandrels, smear effect much smaller for PVD, and also because the sand drain is a mixture of sand and clay, correct? So there is a smear zone is much higher compared to here in this, because here you just push it into the ground in the soft soil, So PVD are consistent factory products, obviously is a factory made, whereas the sand drain is subject to the quality of the variance of the naturally occurring sand. So again, as I mentioned, these are as advantages and disadvantages. I'm not going to go into details over here. This is how it looks like. The PVD looks like. Okay, so these are the the PVD product from the various company. So first one is the cardboard wick. Wick they call it. Is a geo drain. These all these different types of drain. Basically inside there is a high density polyethylene type of material, and then on the top there is a geotextile type of material, so that only the very fine particles of clay should not go and block this drain. Okay? So the clay particle size, that they're less than 2 micron or 0.002 millimeter. So we don't want that. It's a clocking. Although yes, blocking sometimes happen, but you cannot avoid that. This is how it looks like if you see carefully. In bigger scale, prefabricated vertical drain. Inside, if you see the inside, there is a polyethylene core, and then geosynthetic fabric is encased. Okay, so this is how it looks like in actual. The core is inside, and right side over here, geotextiles. So equivalent. So for this, because this is flat, if you know the width is B, if you know the length, thickness, A. Width is A and thickness B, you can find out the equivalent drain diameter. So 2 times A plus B divided by pi. There are several equations. This is the easiest equation you can calculate how much is the equivalent diameter. So basically what is a flat, but how much the area, equivalent area, we are converting that. This is how it looks like, the PVD at the side. So this is instrument, and it comes in a roll over here, and then just push it into the ground. Okay. This is I took this picture, is close to our campus. They have that PVD over here, and there's a rig over here, and you just it comes in a roll over here. It comes in a roll. It can go up, and then there is a metal rod that can just push it into the ground. Okay? So over here it comes in a roll, and then they just attach. When they come up, so they just cut it. And I saw that they just when they attach it, just use 2-3 stapler and then attach it. There is no other method to do that. So you see, just they use staples and then just join that. Okay. So this is how it looks like on the side. And then later on, you have seen that it can be the vertical one. It can be connected to the horizontal one, and put a sand blanket and then put some load over there. Okay. This is how it looks like in the overall. So this is a rig installation equipments, and then from this PVD drain, it can go up and then come down and then put it into the spot. So again, there are mandrel and drain. There are different tests you need to do. And then also that the degree of horizontal consolidation. So this is the equation is given by equivalent drain equation given by Hansbo, and you can find out the time time for degree of consolidation using these equations. Basically, whatever the equations on the top, same equation you can use. You can find out the time here if you know that how much is the horizontal coefficient of consolidation. Then the square grid pattern layout of PVD, you see there's one PVD is here, one PVD here, one PVD here, one PVD here, the 4 PVD. How much, if you know the spacing D, if you know how much is the equivalent diameter, so that's the one you need to calculate the DEU for one PVD. This is the equivalent diameter, so you need to calculate for how much is the equivalent diameter for this, how much is the smear zone, how much is the width, how much is the thickness. So if you know that, easily you can calculate how much is the equivalent diameter. So how much equivalent diameter is how much is that one PVD is responsible for that area to drain the water out. The primary use of PVD to, again, the same thing, primary accelerate the consolidation to greatly decrease the settlement time of the embankment. Vertical drain decrease the amount of surcharge and preloading, required to achieve the settlement. Vertical drains also particularly effective when the clay deposit contain many thin horizontal sand and sand silt lenses. PVD drains are band-shaped product consisting of the geotextiles filter membrane surrounding the plastic core. Dimension of the drain is 100 millimeter wide, 3 to 4 millimeter thick, it's very thin. So it comes in a roll, just easily push it into the ground. The main function of the filter of the vertical drain is to ensure the fine particle cannot pass through and clog the drain. So because it's very, it's a 3 to 4 millimeter thick, and then the coating is the geosynthetic geotextiles layer, so that the clay particles should not block the core of this that PVD. So the main properties of the vertical drain are generally specified in the ground improvement project are basically the discharge. We need to check the discharge capacity. We need to check the properties of the filter. We need to check the tensile strength. I just pause for a minute. Okay. Can you come after around 2 o'clock? I need to check the time also. Okay, just email me. I'm sorry about that. Thank you. Sorry. Can you hear me now? Can you hear me?
Yes, sir. Yes, sir.
I'm so sorry. There are some students there. So as I mentioned, like a vertical drains need to be specified for ground improvement. So a few things you need to check: the discharge capacity, you need to check the properties of the filter and the tensile strength of the core itself. Okay? So discharge capacity is basically the higher discharge capacity, better the performance of the vertical drain, right? So factors affecting the performance of the vertical drains are consolidation stress, deformation of the drain happens, time, clogging of the drain, obviously the hydraulic gradient and the temperatures. Sometimes these are the things may happen. The folded PVD, the purpose is it should be vertical, but your installation somehow it distorted like this because of the excessive compression of the load. So and then you need to check that the properties of filter. So when you talk about the filter, so we need to know that the filter of this geosynthetic material, right? So geosynthetic material, I hope everyone knows that there are two different types of geosynthetic type of material. We will talk more about that. So again, here in this case, the opening aperture you need to check, and then based on that, and you need to know there are different criteria, soil retention criteria. We need to check that the D85 of the soil, And O is basically the properties of the geosynthetic material. So most of the time, the geosynthetic material, whether it is oven or non-oven type of geosynthetic material, there are two different types. Generally, the company will provide all the different properties of the geosynthetic material. Okay? The filter soil retention ability need to be checked, and then the permeability also need to be checked. So obviously, the permeability of the filter, it should be more than permeability of the soil. Otherwise, what is the purpose? So you need to do that. Usually, the soil to be treated by PVD, very low permeability. The requirement should be easily met in most of the cases. And then the clogging. Also, yeah. Really? Oh, now is it good now? So what? Can you see now?
Sir, you can just start
Sir,
sharing again, sir.
Sir, screen is shared. Your slides are not moving. Screen is shared. Slides are not moving.
Oh, so what slide you can see now at this point?
So the main property
27.
of vertical drains, something like that.
So can I just stop share and then do it again?
Yeah, you can
better,
try
sir, better.
that.
Yeah.
Okay. Yeah, I'm so sorry, man, because I paused it, correct? Oh. Can you see now?
Yeah, screen is visible. Just try to, sir, change the slide. Let's see it is changing or not. Yeah,
Now
it's
it's
changing,
moving,
sir.
sir. Now
Yeah,
it's
it's
okay.
okay.
Oh, okay. So I don't know up to what portion you have seen. Like this one. You can see this one earlier. I don't know because I was,
Yeah. This one only, sir. Yes, you were talking on this slide only.
Oh, this slide. Okay, so again,
Yeah.
this is the later on now in this one. Did I explain? But you could not see that, correct?
Yes, sir. It was explained, sir.
Okay, this one explained. So again, as I mentioned, that the PVD, can you see now the discharge capacity, properties of the filter, and tensile strength?
Yes, sir. Yes, sir.
Okay.
Yes, sir.
So I'm so sorry again. The vertical drain. So while doing this, the main properties you need to check when you do the installation of PVD. Discharge capacity you need to check. You need to check the properties of the filter. You need to check the tensile strengths, the PVD itself. Okay? So discharge capacity, when you do this, the concentration stress, deformation stress, time, clogging of the drain, hydraulic gradients, all these things you need to check. And then sometimes, as I mentioned, that the PVD also, because of the compression loads, it should be vertical, but it just folded like that. And that will not solve the purpose. And then also you need to check the filter. And the filter is basically the PVD, just like a flat pipe, right? So inside there is a core, HPDE, high density polyethylene type of material, and the top there is a geosynthetic material, as I mentioned, so that may be oven and non-oven type. So we need to check that the O95 should be less than 2 to 3 times of D85. O95, the aperture opening size you need to check, and then also there are two relations. So O50 should be 18 to 24 times 50. D50 is the particle size of the soil particles. Permeability, as I mentioned, so it should be filter material should be more than the particle permeability of the soil. So the KF for the filter should be 10 times at least for the soil. And then the clogging resistance also need to check depending on the porosity. It should be more than 30%, and O95 should be more than 3 times of D15. So that one you need to check. There are a few criteria you need to check, and then also so that you can avoid the clogging. Okay. So these are the recommendations given by the Wang and Chen 1996. I've just taken from their paper. Tensile strength is also is important. Earlier on the sand one, you see, remember the sand rain, if it is act as a sand column, that is not going to solve the purpose, right? So here, the same thing also, the tensile strength of entire drain of weight should be at larger than 1 kilonewton, tensile strength of 10%. So that is required. Longitudinal strain, that failure should be more than 2%, but should be less than 10%. And any seam in the drain filter should have equal or better properties. So while doing that, the seaming, you need to have the better properties. Okay. So some essential facilities required for the quality control implementation of the for the PVD project: discharge capacity of testing, the straight drain tester; discharge capacity of testing, the bulk drain tester; tensile strength testing, cross plane permeability testing filter, aperture opening size filter. So all these things need to be checked when after installing this PVD. Okay. So again, the idea is the same. PVD for the fine grained soil. Idea is it can shorten the consolidation times, lead the increase of subsurface bearing capacity, because the water is going out, pore pressure reduced, effective strength increase, bearing capacity increase, shear strength increase. Inner core and outer core jacket, the width most of the time there is a different company has different specification. The width is 100 millimeter, thickness is 6 millimeter. Flexible core with form flow grooves on both sides along the line. So it depends what type of pattern they used. And then there's a jacket is only the surface membrane. Okay. And then theoretical considerations. Sometimes we need to, while designing this, the vertical drain, drain spacing, which will be required, degree of consolidation. So again, we need to find the equivalent diameter. So we need to check that. Drain will take place in both vertical and horizontal. Therefore, any design method should take into account the real situation properties. So again, we need to check the horizontal and vertical, because the vertical horizontal permeability stuff is not easy to do. And that's why people are using different correlation. If you know the vertical permeability and how to find out the horizontal permeability. So, and then Barron also given some equation on this based on the vertical sand rain. And then, so basically, you can use that different equations considering that degree of consolidation in the radial directions. And so you can calculate how much would be the consolidation or consolidation for this, or degree of consolidation when you use PVD or when you use sand rain. Only thing is you need to check that what pattern you used, whether it is sand rain or PVD, and then what should be the equivalent diameter. If you know how much is the equivalent diameter is covered for a particular sand rain, if you know the whole area, you can find out how many sand rain you need, and then you can design accordingly. Okay. So I think that's all for this PVD and sand rain. And now I'm going to solve some of the problem. Okay. Anyone has any question on this? So I know that I just go quickly. All this, whatever. Can you see the screen now? Can you see the screen?
Zoom is written on the screen, right, sir?
Whatever. Can you see now?
Yes, sir. Slides are visible again.
Slides are visible.
Okay. Okay. So anyone has, so do you think I should solve the problem? So anyone has any questions on this? So we talked about sand rain, we talked about PVD, and then also the sand rain. There is sand rain also, which is like a geosynthetic encased sand rain. There are 3 different types of vertical drain. And then basically idea of this PVD sand rain or geosynthetic fabric encased sand rain is idea is rate of consolidation is increased basically because of this, not only the vertical the drainage, there should be water can flow in the horizontal direction or radial direction. That's all. You think I should, anyone has any question? Otherwise, I can share the problem and then I'll try to do, share the screen. Maybe I try to solve this. What do you think? Okay. Okay. So, but we need to use this. I mean, how do I can do that? I mean, share the screen also, and then also equations and everything. But anyway, first thing is let me have to stop share. Can I share two screen at one time? I don't think so, right? In Zoom. Oh, okay. All right, so I just stop here now. And, the file first. See now? Can you see my screen?
Yes, your board is visible.
Word file, right?
Yeah, word file is visible.
Okay. The size maybe. Okay,
Yeah, this size is comfortable.
Huh?
Yeah, this size is comfortable, sir.
Okay. So, I have few problems. It's very simple problem. So just for example, I'm not going to solve any problem like a for a well point test, right? Well point. So most of the time, we depending on this unconfined aquifer or confined aquifer, and you know how much is the drawdown. If you know the permeability, and if you know that the observation wells, how much is the distance from the center of the well to the observation well, center of the well to the second observation well, and then you can find out that how much is the drawdown. Basically, how much is the the drawdown inverted cone, how much is the area of influence, and how much is the drawdown, each drawdown for the first borehole, observation borehole, second observation borehole. And then you can easily find out that how much is the discharge. And then from there, you can find out the probability. So it's very easy. That one, I'm not going to solve anything. And same thing for if it is confined aquifer, you can use the equation, you can easily calculate. And then only thing is the difference is there are, I have not added that part, like if the borehole is installed the fully penetrated or partial penetration, or the steady state, the flow is not occurring. It's an unsteady state. Then the equation will be different. If it is a partial and unsteady, there will be a different scenario. So same thing for confined aquifers, same thing for unconfined aquifers. But that one, it's a different equations only, and you can easily calculate. So first problem is here, well point system used to lower the groundwater table, stratified medium sand. What is the required spacing of the well point according to NAVHAC, design chart? So, I should have given this problem earlier. So then you could have this problem earlier, and then I can, share my screen and see what I can do. So what I can do now, not PVD. So there is a design chart, actually. You need to use that chart. So here the water table is 5 meters stratified sand, medium sand. So you need to, that 5 meter, and you need to use that the sand, why is the sand located, and just draw a straight line. And from there, you can easily find out that how much is the spacing between this well point. Okay. How I can do that? You need to see the chart, and then only you can find out. I can stop share then, right? And the second, so the first problem is very easy problem. You need to see, I have morning, I explained that chart. There are two charts. You use that chart. So how much is the the first column is that the groundwater table, and then easily you can find out what type of soil. You just draw a straight line where it meets in what type of soil. Easily you can find out. Second problem is basically, that the multi-wells are used for the dewatering and excavation site. Dimension of the excavation feet is given 125 and 200 meter. Height of the phreatic line above the impermeable layer is pumping is given. Height of the phreatic level of the center of the excavation pit is after pumping is 6 meter. Permeability of the soil is given. Well diameter is given. You need to calculate, determine the number of wells required for this dewatering project. Okay, so this it stops here, but you cannot see the problem. How any idea how we can do that? Because I should have sent this problem earlier. Any idea?
But if share entire screen, it may help that two windows can be opened at once. It may help, sir. I'm not sure.
Two windows can be open. Can I need to attach something like a, write something, right? Yeah, what is that? Yeah, I have more options. More, right? It's record. Oh my gosh. I have to do that. Ah, any idea, anyone? Oh, I tried earlier. Let me just stop share now and then try again. I'm so sorry.
डायपर साथी है के डे
The new whiteboard.
सुपर रखे को डायपर
Yes.
कद को पेरेडो छोरो
So can you see now the whiteboard? Now you can see the whiteboard. Somehow put it in my screen here, right? What do you- This one. Post this one to my screen here. So, I don't think it's going to work. So what, I don't know why it's not working. What I can do, maybe, I just take every individual problem and then solve it and then just post it. What do you think? Whiteboard is option is showing there, but I need to put it in my, like I have a tablet type of stuff here, and it should come here, correct? Unless otherwise I cannot write it, correct? Yeah, so that is it's not, I don't know why it's not working. Yeah. That whiteboard is, I open new whiteboard. So how to move to my screen, So
sir,
it should
or else
be
what can be done? A white this.
what? Come again?
I was suggesting that white screen in a PowerPoint presentation can be opened and you can write on your tablet with the help of that. That can work, I guess.
Presentation. And but I need to try. Okay. But again, you need to have the problem first, right? Very easy. So you are telling like, hey, just open any PowerPoint.
Yes, blank PowerPoint.
Blank PowerPoint.
Yes, there you can write, sir. I tried it once in with my students. It worked.
Okay. What? Okay. Yeah, I'm not very good in this. We use this one, and then now I just forgot. So what can you see now? Can you see the PowerPoint or? Okay. Okay. So can you see now something? So this is a different thing. So I need to just stop share now and open another file. Okay. Okay. But you need to see the problem also, correct? So share. So you see like, okay. So can you see now? Okay. Can you see now? But if I write something, can you? No? Oh, okay. Okay. Oh my God. So this one I'm not used to. Okay. All right. So for this the multiple well, but the only thing is you need to see the problem also, right? So how I can share that problem? So what you can see now, so you can see only one screen, correct? Hello.
Yes, sir. Only this blank
Yeah,
PPT is
it's
visible.
only the
Yes.
blank PPT, but I need to, because you don't have the problem, correct? So I'm just writing the problem maybe here. So basically, we have a dimension of, again, why is not? Dimension of a excavation site is given like a 150 meter times 200 meter, 200 meter, and the height of the phreatic level is above the impermeable water layer for pumping is given, and that is 15. So before pumping, I'm just writing before pumping, the water level was 15 meter. After pumping, so is 6 meter, and then permeability of the soil K is given is 2.3 times 10 to the power minus 5 meter per second, and the diameter of the well, diameter of well is 200 millimeter. So we need to find out that number of wells required, basically number of wells required. That's the problem. So first thing is what you need to do, you need to find out, because the dimension is in like this, in the square rectangle. So what you do first, you have to equivalent diameter. So first thing is we need to do equivalent radius, you need to find out. So you need to find out what is the equivalent radius of the excavation. So we need to calculate first. So that is R naught is the square root of, how much is the length and width divided by pi. So if I say, so this is, so anything is A and B, so easily you can calculate how much is the equivalent. So 150 times 200 divided by the pi is 3.14. So easily you can calculate that this is 97.7 meter. Okay? That one you can calculate. So now you need to calculate, that is the equivalent radius. So now equivalent, how much is the radius of influence is going to calculate in the PowerPoint slides. I already mentioned. So there, this one, it should be the influence radius. This influence radius. So is Ri given by this equation C prime HW0 original height HW1 square root of K, right? So then so you can calculate that. The C is, you can calculate, there is a standard value you need to take. So in the PowerPoint slide you mentioned, so for different well point system, if it is a single or multiple, so we have like a range around 3,000. And then HW1 for this case, initial before pumping, it was 15 meters. So this is the 15 meter minus HW after pumping is 6 meters. So use that. And the square root of K is given 2.3 times 10 to the power minus 5 meter per second. So you can calculate over here, it is 129.5 meters. Okay? This is the one first you need to calculate. So now you need to calculate the discharge. So how I'm going to do that again? So I have to put a different. Another blank slide, sir. How do you do that again? Oh my God. Yeah, it's good. I think it's good. Okay. I'm so sorry. So then the total discharge, you can calculate. Total discharge is dq using this equation again, pi times k hw0 whole square minus hw1 whole square. So can you read it, whatever I'm writing?
Yes, sir.
ln ri divided by r naught. So not very good. But anyway, so this is pi times k. Pi is 3.14. Times k is given 2.3 times 10 to the power minus 5. This is 15 square minus 6 square divided by ln. Ri is already in phase radius. That is the one we already calculated, 129.5. And then R naught is the one, is the equivalent radius. Equivalent radius we calculated already. That is 97.7 meter. So only thing is here the ln is base E. So you can calculate that. How much is the discharge? So if you calculate, this will be 0.0458 meter cube per second. Okay. So now this is the total discharge. This is the total discharge. Now you need to calculate how much is the discharge from individual well. Okay, so you need to calculate the discharge from individual well. So QW1 easily you can find out pi k, the similar type of equation, HW0 square minus HW1 square divided by ln is Ri divided by R naught 1. So that is the only thing is the difference, that individual diameter of the well. So you can calculate that, everything. So whatever this is, pi is equal to 3.14 times k is the same, 2.3 times 10 to the power minus 5. HW square, H is here, how much? Is the same, 15 square. How much is that? The drawdown 6 again, ln. How much is the R1? Ri? The 129.5. And how much is the RW here? RW? We mentioned earlier this one, correct? Initially. How much was that? You know, the well diameter, it was given 200 millimeter. 200 millimeter, the well diameter. So how much should be then the value of this one, RW1? So 200 millimeter diameter. So radius should be, this is radius, correct? R01. Radius is 100 millimeter. And then the meter, you convert it to meter. So if you, then it should be 0.1, correct? So 0.1 meter. So then the discharge is 0.0191 meter cube per second. Okay. This is the discharge for the individual well. Okay? So we need to calculate how much will be the number of well required. So number of well required. So you can calculate number of well required is how much is the total discharge, correct? Q UW calculated divided by how much is the individual UW1. So easily you can calculate that. So 0.084 divided by 0.019. So that will be approximate 26. Approximate 26 number of wells is required. Okay. Yeah, I should have given this problem earlier. So now I'm just going to write the problem here itself. So there's no point of showing that. This is all right. So it will take more time with this slide. So is it good now? The first problem, second problem, basically. Okay. So the equation will be given. We need to find out how much is the influence for one well. Okay. And then you calculate that the discharge, how much is the well discharge, equation is given. And then you calculate, the only thing is well diameter is given. So easily you can calculate that, how much is the equivalent diameter. And then the total discharge, how much is the individual discharge. So total water, total discharge is this much, individual well is this much. So total divided by individual one, then you can number of wells. The second problem is, we have here is the surcharge problem. If you have a surcharge, then what is going to happen? So I'm just going to draw a little bit of that. This is really so small. So so here, to show you the figure. Without figure, it will be difficult. Just go here. I want to just stop share, and then again I do. Can you see now the problem? Okay. So this problem over here, because I'll be using the graph and charts also. I don't know how I'm going to do that. So here, this problem, there is a field operation takes place, and the average permanent load is given on the clay layer is 75 kilonewton per meter square. Average effective overburden pressure is given for field operation is 110. Height of clay layer is given is 8 meter. CC is given, E0 is given, CV is given. So first thing is primary consideration settlement caused the addition of permanent load. Okay. So you need to find out how much is the primary consideration settlement of the clay layer caused by the additional permanent load. So that one first thing. Second is how much the time required for 80% of primary consideration settlement under this additional permanent load. And the third one is, that the permanent surcharge that will require to eliminate the entire preliminary load. Okay. So first problem is basically what you need to do, because it's a normally considered clay, correct? You see here, normally considered clay, and then we find out how much is the settlement required. Okay. So, and then, so that's the first thing is you need to calculate how much is this is the primary consideration settlement of clay layer caused by the additional permanent. So first you calculate the primary consideration settlement. Okay. So I'm just going to stop share now, and then again I just want to share this. Okay. Can you see now my PowerPoint slides? PowerPoint empty one. Okay. So here, the first thing is you need to calculate how much the settlement. So primary consideration settlement is basically So primary consolidation settlement, first thing is, the settlement, and due to the primary consolidation is given by this equation, Cc times H of height of clay layer times 1 plus E naught, initial void ratio, log of 10. This is sigma 0 prime plus delta sigma pressure divided by sigma naught pressure. So easily you can calculate that. How much is that? The settlement. Cc is given for this case. I'm just going to write here. Cc is given 0.27. Height of clay layer is given also. So that is 8 meter. Okay. Height of clay layer is given. Then initial void ratio is given E naught. That is 1.07. 1.02 is very high void ratio. Void ratio is generally in fraction, right? For the clay, it is much higher. Coefficient of consolidation, that is 0.52 meter square per month. Okay, that's given. So again, what I need to do, just plug it in all these values. The Cc is 0.27, Hc is given 8 meter, 1 plus E naught, so 1.02 log of 10. Sigma naught, that one you need to calculate how much is the pressure. So initial pressure was 110 before fill. So that is given already in the problem, 110. And then how much is the increase in stress, that is also given after this, the fill operation. So it is given like a 75. And how much is the initial stress is 110. So easily you can calculate how much is the settlement. So settlement, if you calculate, this will be around 0.241 meter. Okay. This is the settlement, the first part of the problem, initial settlement. Okay, you can calculate. So now you need to find out the time to 100%, 80% consolidation. The time required for 80% consolidation, the settlement under the additional permanent load only. So what do you need to do? We need to find out the time factor, that is TV. TV is equal to what? CV times T divided by H squared. CV is, and then it says degree of consolidation is 80%. Degree of consolidation is 80%. So when the degree of consolidation is 80%, there is a relation between this TV and EU, and there is a standard charts or tables are available. So you can find out from there, either use equation. So when EU is equal to less than 60%, then TV is equal to pi by 4 EU by 100 whole square. So that is the one. Another one, if it is more than 60%, there is another equation to find out the TV, the time factor. So you can use the standard table also to find out. For 80%, I'm just going to write that 80% from the table, TV or time factor is 0.567. So you need to find out the time over here. So you need to find out what is the time over here, T. You need to calculate. So T is basically how much is that time factor, that is 0.567. How much is the height of drainage? That also you need to know how much is the height of drainage. Here in this problem, the drainage is both sides. So the height of clay is 8. So HDR would be how much over here? Height is 8 meter. So how much is the height of drainage? Because in two-way drainage, right? In this case. Yeah, it should be 8 by 2. So it should be 4 whole square. Okay. And then divided by CV, correct? So T is equal to T times H divided by CV. CV is equal to 0.52 meter square per month. So easily you can calculate that the time, because everything is in meter square, and then CV is in meter square per month. So this will be time will be in month, right? So it will be 17.45 months. Okay, this is the one that the third problem is, if the temporary surcharge will be allowed to eliminate the entire primary consolidation settlement in 12 months by the pre-compression techniques, then how how much will be the the load you need to add. Okay, so that all the primary consideration is going to occur. Okay, so insert here. So first thing is what I need to do. We need to find out that the time is. So it is in the problem. It is given consideration temporary surcharge delta sigma f that will require to eliminate the entire primary consideration settlement in 12 months by pre-compression technique. So again, you need to see the figure and graph. Unless you do that, you cannot really. We'll be using some figures and graph. The graph. So basically, what you need to do for T basically is 12 months, okay, for 1 year. And then you need to calculate how much is the TV. So TV is equal to, again, CV times time 2 divided by H squared. Everything is same, like a CV is equal to 0.52 meter squared per month. And then a TV is equal to 12 months. And then HDR is equal to the same, that 4, 8 by 2, 4 squared. And then you will get around 0.39, right? So for now, for the TV is equal to 0.39, you can calculate how much is the value of U from the table. So easily you can calculate that, and it will be around 53%. Okay. So now you need to use that delta sigma P prime divided by sigma naught 0 is how much. From the graph, you need to calculate. So we know that sigma initial pressure was sigma 75, and then this was 10, 110, 110, like earlier one we mentioned, right? So, oh, sorry, this one. Over here. So 75 and 110, that's the one we mentioned. So you're using the same values over here. So you're getting around 0.682. And then there is an equation to use to calculate that how much will be the sigma delta sigma final effective pressure. So this one you can calculate using a standard equation. So you can calculate that that the TV is equal to, this is a long equation, so you can use that equation, so you can easily find out that how much will be the sigma pressure. Okay. So without sharing this screen, it is difficult. So I don't think is it make sense. I'm just the way I'm doing it now. Does it make sense? And the way I'm doing, because you're not seeing any figures, anything that chart I'm using will be using. I don't think it makes sense, man. It's just like a one way. I mean, is there any other time we can do that? I can stop here today, and then I'll send the problem first, so everyone has the problem, and then I can just do that, or I'll check this one. Not using this PowerPoint. Why it is not working? I don't know. So, do you think that is it good, or do you have some other time to do that, or what do you think? I mean, this is I'm not feeling good. The way I'm doing it. Tomorrow we have some other things to do also, right? So many other topics. I don't know. This is the way it is going is not good. I know that tomorrow morning there is a class, correct? Salt stabilization stuff. Then Okay. Okay, I'll take some time there, or maybe I can finish some early, that the other thing. So this is, yeah, I mean, yeah, go ahead. Yeah, I think so, because I'm not very comfortable, and the way it's going on, it is like, it's not very good. Okay, I hope I can figure it out. Okay. All right. I mean, I'm extremely sorry for this inconvenience. All right. Thank you so much. Okay. Yeah, yeah. Can I just send it to you guys? Yeah. Okay. Okay. I'm going to do that. So that will be quick. If you have if everyone has that copy of that the problem, and then I just solve it. But this one, I'm not very comfortable with this PowerPoint stuff. I need to use that. Why I don't know why it's not working. I have a big screen. I mean, that one I can write it. I used to do it during online classes, but I somehow we use the anyway. All right. Thank you so much. Sorry for the inconvenience. Okay. All right. Okay. Bye.
Thank you, sir.